Hello, can you all hear me? Give me a nod. Say yes in the chat, abuse me. Whatever it's going to be. Hello, can you all hear me? Give me a nod. So I know that in the background there's a little bit of fan noise. Okay, yeah, there's going to be a little bit of fan noise in the background. I'm yet to get a better microphone that cuts out the ambient noise, so you're stuck with the one that actually works. I'm running on Linux, that's part of the problem. But yeah, hopefully we won't have any problems with the audio. I'm also going to put on another backing track similar to the one that I had on last time. If it gets too loud or too annoying, then let me know and I will switch it off. I would try my best to keep my eyes on what you people are saying as we go and answering your questions. There's some people chiming in through ulterior means. Okay, so right, so what we're going to do today is I've got two binaries sitting here that were used as part of the B-Sides Canberra CTF earlier this year. Oh, by the way, don't forget your T. Hacking without T is uncivilized. Greetings all. Thanks for coming. So yes, the first binary we're looking at is something called guessing. It was written by a chap called Peleus, who lives down in Canberra. He's a good mate of mine. And it was intended to be kind of almost like a baby's first SRP, stack buffer overflow style exploit. And it's got an annoying little thing in front of it that you've got to get past before you can get there. So what we're going to do is we're going to have a look at that one first. I'm going to try and get through that one a little quickly. I'm not going to rush it, but a little quickly so that we can move on to the second one. So after we've done that one, I'm going to move on to this other one, which is like guessing 2, and it's based on guessing. Does the same thing, it just has one important difference, and that is guessing does not have NX enabled, which means that the stack is executable, whereas guessing 2 is basically exactly the same binary. The only difference is that NX is enabled, so we can't execute any code that we put on the stack. Yeah, daylight savings. Hopefully that's going to save you with the B-Sides, the SecTalks Canberra people who may just join us a little bit later on when they finish their SecTalk session this evening. Right, so first thing we're going to do is I'm going to run guessing and show you what it does. You see, first of all, it just asks for a guess. I have a number between 1 and 100, so we'll do the classic sort of binary search. 750, 825, let's go 920, lower, 8, lower, 850, lower, 840, lower, 830, 835, 837. But hey, okay, so there's a fairly standard number guessing game where eventually you've got to you find out what the number is, and then it asks you for your name and it'll schedule a meeting. I think that's a little shout out to Switch, who's a friend of ours. You want to increase the font size? Yes, I can do that. We have the power. We can increase the font size. Where are we? Profiles. Let's bump that up to monospace 13. Yeah, how's that? Is that better? You can see that a little more clearly. So that means let's do that. Is that a bit better to read? It looks a bit better, so we'll stick with that. Okay. So once we've got this prompt, we can type in whatever we like, and the game ends. Realistically, I mean, there's obviously only one sort of major point here that we would look at from an exploitation perspective. And that's right at the end there where it asks for a name. So what I'm going to do is annoy you guys again, and I'm going to do this quickly. Higher 850, higher 900, 875, 850, I've already done 850, 860, 865, 870, 72, 873, 74. Okay, so now instead of just entering a normal name, I'm going to put in something a little bit bigger just to see what happens. Hooray! As we can see, there's a seg fault, so that clearly means that we've given it a little bit too much information and it hasn't known how to handle it. So what we're going to do now, rather than just dive straight into exploitation mode, we might just have a quick look at the source code using Binary Ninja. Before you guys ask, this is the biggest font size that I can use inside Binary Ninja. From what I can tell, like zooming in any further doesn't make it any bigger. I will look perhaps later on at changing font size through some other means, but for now this is what we've got. So as you can see, this doesn't have symbols stripped too much. Here we can see our program entry point calling main, and main is actually fairly trivial. So just a quick scan through because I don't want to hang around in this particular binary for too long. To begin with, what we're doing here is we're marking standard out so that it's not buffered. Instead of buffered, it outputs or flushes the buffer every single time a single character is written. So that's what the setBuff call is doing. As you can see here, we've got this call to time, srand, and rand. And that's probably the fairly classic randomization and initialization that we see, where people call srand time null in order to set the seed of the random number generator based on the current time. You have a discount code for Binary Ninja? No, I'm afraid I do not. So anyway, we set the seed for the randomized timer, and here you can see we're doing the please enter your guess. It's printing that to screen, and then it reads in a character, a value using scanf. And if we have a quick look at the value that's being pushed onto the stack here, you can see that it's just %d. It's just raw text, so nothing too special in there. So we're printing out a message that says please enter your guess, and then it reads a single integer using %d and scanf, and then from there it's just doing a fairly trivial loop to determine, have you matched the number, or do you need to guess again? So that's what these comparisons here are doing. So this first comparison says if you've gone too high. If you haven't, it'll go this way. Sorry, if you've gone too low. If you haven't gone too low, it'll go down this branch. Otherwise, it'll go to this branch and say you need to go higher. If you've gone too high, it will then take this branch and say you need to go lower. Otherwise, it's probably fair to assume that you end up calling win. It's doing another check here to make sure that the values are exactly the same. And if it happens, it calls this win function. Wish I knew about talking cons. Okay, so this win function calls putS, which just says, yeah, you've guessed correctly, and then skipping all of this getChar stuff. It says, please enter your name and we'll schedule a meeting, and then it calls getS. And getS is being called on this buffer here, which is a stack buffer. And you can see that getS is basically something that will read until it reaches a null terminator, I believe. But in order to validate that, let's fire up Chrome. So I'm going to kick off the music in the background now. If it gets in the way, let me know. I'm going to turn the volume down a little on my side, so I can hear myself think. Anyway, if that noise is too noisy, then please let me know. Will you also share the binary source of guessing program after the session? Yes, absolutely. I will upload both of the binaries, and I'll even share my exploits with you so you can have a play with them. All right, so if we just look at the function getS, you can see, according to the documentation, that getS receives a single argument, which is the buffer that's going to contain the string that you're going to write to, which is just here, right? And it will keep reading from the terminal until it reaches a new line character. So as you can see here, keep copying until you reach a new line character. So clearly that indicates that as a result of us typing in too much stuff here, we've probably gone well and truly over our stack buffer. So going back to our stack buffer, we can see that there's probably only, where are we? I guess based on what we're seeing here, there's hex 98 characters spare. A little bit more than that, and we'll end up overriding our the end of our buffer and doing all kinds of horrible stuff to the stack. Right, so just as a quick recap, we need to remember that when a function's called, all of the arguments are pushed onto the stack. This is in 32-bit, by the way, and I'm sorry I didn't make this clear, but this is a 32-bit binary. Hopefully you guys would have guessed that based on the fact that there's no evidence of 64-bit registers in the dump. So in a 32-bit program, arguments are all pushed onto the stack in reverse order. After that, the return address of the address basically where the code needs to return to when the function is finished executing then gets pushed onto the stack. And then the function gets called. So control is passed, let's say in this case, to this push line. And push says push EBP onto the stack, which is the current base frame pointer. So it writes that to the stack. And then the next thing it does is it takes the current value of ESP, which is at the top of the stack, and copies that into EBP. So that's effectively moving the bottom of the current stack frame up to the start of a new stack frame, and then it subs a value from ESP, pushing ESP further away, which means we're kind of allocated a whole new stack frame on top of the previous stack frame. And then when we get to the end of the function, we can see there's this fairly typical leave ret style pattern. And leave is kind of like a synonym or an alias, shall we say, that does exactly the same thing as move EBP into ESP, which basically moves the stack frame down, pop the value of ESP into EBP, so that moves EBP back down to the bottom of the previous stack frame, and then we call ret. Okay, so that's just a fairly typical function prologue and epilogue. When we come in, we do a bit of pointer juggling with our registers, allocate some space onto the stack, and that's where all our local variables are actually going to be kept. And then we do the reverse when we finish up at the other side. So this is clearly the vulnerable function as a result. Probably there's not a lot of binary analysis that needs to go on here. I just wanted to show you where this function is actually vulnerable. And clearly it's this getS call, which writes to the stack, and if we punch in more than hex 98 characters, we're going to end up going past the end of our buffer into other local variables. Eventually we're going to keep writing past those variables, and we'll end up going over the top of what is currently the saved base pointer for the previous stack frame, and then followed by the saved return pointer. And that saved return pointer is going to allow us to pass control to various other areas in memory. So what I'm going to do now, because we've got this annoying guessing game in the way, we're going to automate this pretty much out of the box, because I really don't want to have to type these values in every time we play the game. So I've got my crappy little Python stub sitting here, and the way I like to write these exploits as I go is I'll fire up the app behind the scenes, and then I'll give myself the opportunity to attach to it using GDB. And once I've attached with GDB, I'll then continue running the program, and then if I get a crash, I've actually got a debugger attached to it. Now I know using things like tmux and screen and other tools inside pwnlib, I can automate that process, but I haven't at this point bothered doing that. Okay, any questions? Please feel free to sing out as we go. Right, so what I'm going to do, I'm actually going to start by creating a function which is called, we'll call it play game. And play game is going to take a copy of the program instance that we're currently interacting with. And I, for some reason, always call it S. And I think it's because in my mind, I'm talking to a socket because it's something that I'm attacking remotely. And even if I'm attacking something locally, I've kind of just translated that to S. So just down here, you can see I've just got this stub where I use the pwnlib to create an instance of the process and attach to it. And S will then contain a reference that we can actually talk to the program through. So looking over here, we can see the first thing that it says is please enter your guess. Oops. Please enter your guess followed by a prompt. So the first thing that we're going to do, I'm just going to do a nasty while true loop, and I'm going to say s.recv until, and we're going to go all the way up until we reach the prompt and throw everything away. Now, as we're looping through, we're going to need to know what number it is that we guess last, and we're going to have this sort of sliding window of low and high. So what we'll need to do is we'll have a low which starts at 1, and we'll have a high that starts at 1,000, and our current guess, which is going to be in the middle of those. So that's what we're going to start with. So when it asks for our first guess, what we're going to do is we're going to say s.send, and we'll send in whatever number it was followed by a new line. So format whatever our current guess is. Okay, so that will send through our first guess, and then it will respond to with you need to go, a higher or lower. Okay, so the next thing we're going to need to do is actually read. I need to increase font size again, do I? Oh yeah, I'm in Vim now, sorry about that. Just give me a second. No, I need GVMRC. Actually, can I? No, I can't. Equals, what am I using here? I think it's source code pro. And I need to set it to, what is it, H14 or something like that? I think that's how it works. Let's just see what that does. No, it's ugly. Maybe I need to choose a better font. What am I using for the terminal again? Sorry about this. Monospace. Close that off. Yeah, it's not that much better. I don't even know what the default font is. Let's just go with that. And tell me if that's any more or less readable, and I'll change it if it's worse. But in the meantime, I'm just gonna push on ahead. Okay, so we send our guess. The next thing we're going to do is get a response, which is s.recv line. So that'll give us everything up to and including the new line at the end. And because I don't want the new line at the end, is that worse, is it? Okay, just give me a second. I'm going to use the font picker in here. Pick a better font. Let's go with... Any suggestions? Yeah, I would recommend you going full screen because I don't usually like to muck with this kind of stuff. Let's go Deja Vu Sans Mono and see what that looks like. Deja Vu Sans Mono. Maybe if I just make that 16. And let's open that up again. Is that any worse or any better? It kind of looks the same, doesn't it? Deja vu sounds mine. It's as if it can't find it. Okay, just give me a second. I don't really like mucking with fonts halfway through. What I'm actually tempted to do is, oops, wrong one again. GVMRC. I'm tempted to just change it using some kind of hotkey. Okay. Sorry, people. Let's see if this works. Can't seem to increase it. Why not? Alright, look, I'm going to be painful, I'm afraid. I'm just going to stick with what I've got now. Otherwise, I'm just going to spend the whole stream mucking with my font. My apologies. If you can somehow increase screen size or something, that would be really good. Anyway, let's just move that back up. Right, okay. So we're going to read the line in, and we're going to strip the trailing new line. Yeah, Zmiriax, I do the Control Plus thing and that doesn't actually do anything. I'm not using a magnifier either. Okay, so we're going to strip that new line off, and then what I'm going to do is I'm just going to split it on spaces. So we can convert that to an array, and then I'm going to get the last space. Okay, so that should contain the word higher or lower. So, unfortunately though, if we look down here, you can see that there's a blank line for when you guess correctly. So the first thing we're going to have to do, instead of splitting, we're going to have to go if response equals blank, then we've effectively won. Else, if, actually we'll do an else and we'll break it up from this point. So we can say, we'll go direction equals the response dot split. Split it at spaces, get the last one. And then we'll go if direction equals, is it lowercase? Yeah, higher. Then what we need to do is we need to move higher. Then we need to take what our current value is and move the low value up and then get the next number sort of between those two. So if we're going to go higher, we're going to set low is whatever guess is, right? Else, high is, we need to go lower, so we need to bring the high end down. High equals whatever the guess is, and then after that, we're going to rearrange our guess. So, our guess is going to be whatever high plus low divided by 2 is. Now, if high and low are even and odd, then we end up with the decimal number. So we'll make sure, we'll force that to be an int, because that would be annoying. So that's what our next guess will be. So instead of passing, what we're going to do is we're going to break out of our loop. And from there, we're just going to return to the caller. We'll let the caller handle it from that point on, because the whole aim of this play game function is literally to play the game to get to a point where we can pass control back to the caller. Okay, so once we've Just put a comment in here. Create an instance of process to play with. Wait for GDB to attach. Skip past the game. So here I'm going to go play game. Oops. Play game. Yes. And then once the game has been played, we're going to go interactive. So we run it now. I'm just going to skip attaching at this point and see what happens. Okay, response. I've obviously typed something incorrectly. I've typed a response instead of a response. Okay, oh, look at that. So straight up, it's played the game very, very quickly for us. And we're already at the enter your name so we can schedule a meeting stage. So that's awesome. Our play game function clearly has done exactly what it is that we want it to do. So from here, we're going to throw away a bunch of other stuff. We're going to go recv until, and it's asking for meeting followed by a colon and a space. So at this point, we know we've basically read everything in from standard in, and we're ready to send some data. So s.send, we're going to send a bunch of A's. Let's do 110 A's in hex, followed by a new line. Hopefully we'll see a crash. Now I'm going to run the exploit in this window, and I'll attach to it in this other window here. So let's do that. I'm going to go GDB attach to the PID of guessing. Continue. Ready? Boom. So there we go. We've sent a long string of A's, and as you can see from the current state of the registers, we've smashed over the top of EBP. We've overwritten the save return pointer, and then when the function has returned, 4 A's have been popped into the EIP register, at which point we've crashed because clearly 414141 is not a valid address, and it can't execute from an invalid address. What do we got here? Alex, could you also find the random value straight away by looking at what rand returns at that second? Well, yes, you could probably do that as far as if you were orchestrating the thing directly locally. The assumption here, Alex, is that this will be running remotely, so we won't actually know what that random seed is. We won't be able to introspect anything from memory. We kind of need to assume that the binary is going to be running on a different machine. So that's why I haven't taken that approach. I hope that answers your question, by the way. Okay, so this is all well and good, but unfortunately it's not very useful given that we don't know exactly how far it is into this buffer that we need to break into to be able to figure out exactly where inside that buffer the various values for EIP, ESP, EBP, etc. all point to. Now there's a bit of a hint here given that there's 124 times. A bit like why it hasn't patched out a guessing game. Yeah, exactly. That's exactly why I haven't patched it out. I'm trying to stay true to the fact that it was as part of a CTF and it was running remotely. Yeah, keep those questions coming, mate. Right, what I'm going to do now is we need to figure out, based on pattern offsets, exactly where something is. Now, here's a strategy that I like to employ, which I recommend you guys doing as well. I create a function called readFile, and you give it a path, okay? And all this does is you say, with open path read binary as f, return f.read. And that basically gives you the ability to read the entire contents of a file in binary format into memory with a single function. And so what I'm going to do down here is I'm going to go to my code folder, go to Metasploit, Tools, Exploit, and I'm going to call pattern create. And I can't remember what the parameters for this are. -L because they're new. And I usually do something quite big, like let's go 1024. And I'm going to redirect that to where I'm keeping this stuff, which is in /stream. I'm going to call it pattern.txt. Okay. Now the reason why I do that is because I like to read a whole pattern into memory and use it as a variable. So before even kicking this off, let's do this. Load the pattern from disk. So pattern equals read file. We're going to assume we're in the same folder. We're just going to read pattern.txt. Now from there, instead of sending a bunch of A's, what we can do is we can just say send the whole pattern, but we know that a certain number of bytes are required to overwrite. The value that we used before was hex 110, so we'll just take the first hex 110 characters of the pattern and we'll throw that in. So that means we're taking the Metasploit pattern, loading it into memory, and we're going to use that as our payload next time. Okay, so I'm going to leave that screen just there for a sec because I'm going to use pattern offset in just a minute to figure out exactly how far. So let's run the exploit here again. This time we'll attach again, continue, and continue. So as a result of running the exploit this time, we can see that our pattern has actually been passed in. We can see EAX even points directly to where the pattern is stored in memory. We can see ESP is pointing to a different location. And we can see that EIP contains capital A, E8 capital A. And so we can use this to figure out exactly where we need to be. So pattern offset takes a Q parameter, and we can paste in A, E8A and ask pattern offset just how many bytes into the buffer this thing is. As we can see, there's an exact match at 144 bytes. Now, I should probably add that the pwnlib that we're currently using at the moment has some cyclic stuff built in that will help us do this stuff on the fly. I haven't played with it much myself, and I don't know it as well as I know the Metasploit option, which is why I've just gone ahead and done this in this manner. So what I'm going to do now is we're going to go back here and we're going to say the SRP offset equals 124. So we know that the offset from the start of our buffer all the way down to the point where the save return pointer is overwritten is 144 characters. Now I can get rid of that window. So this means we're going to start creating I like to call it buff for buffer. We're going to say let's have a certain number of A's. We're just going to start with SRP offset. So that should fill up the entire buffer with A's right up to the point where the SRP value is stored. Then we're going to overwrite that with B's. So there's 4 of those to fill in the 4 bytes for the register. And we'll just add a few other C's for the sake of having something afterwards. And then here, we'll just send the buffer that we've generated. Okay? So this is an attempt to make sure that we know that we've mapped exactly where things are in memory, and that we know that we can pick the exact offsets that we're looking for. While I've actually got this currently being debugged, if I run checksec, you can see here, this literally has no protections enabled. There's no stack canaries, there's no fortify. This is the kicker here. There's no NX, which means that we can execute the stack. There's no PIE and there's no railroad. So this is the weakest possible binary that you could attempt to have a go at. C is just glorious, isn't it? All right, let's run it again. Run it again, attach, continue, and boom. So, EBP, immediately before our save return pointer, contains 4 A's, which one would assume is the end of the payload that we've set up prior to the save return pointer containing 4 B's, which is exactly where we thought it was going to be. And then from there, you can see the C's kick off and carry on further off into the stack. So we are at a point now where we know we can generate payloads that target particular areas of memory that will contain values that we can control. So that's pretty exciting. The question is now, what do we do with it? Well, we do know for sure that we've got 2 current reference points to the stack, right? We've got EAX, which points directly to the first set of A's that we've got. We've got ESP, which points to the C's. So there's two registers here that we know point to areas of memory that we control. So what we want to be able to do is we want to find something inside this binary that's going to give us a means to change the flow of control so that the code or the values that we've passed into memory actually get executed rather than the code inside the binary itself. Now, I think Header has something in here for us. I can't remember because I haven't used this this particular feature much myself, but I'm pretty sure, here we go, jump call. So we can go jump call, and I think it expects, there you go, look at that, call EAX, call EDX. There are a bunch of values there that we know that we can use to pass control to a register. Now, as you can see, there are a few cases of call EAX, and given that we have the ability to control what EAX contains, we're actually in a pretty decent position. So what we'll do is we'll steal one of these addresses. Now, thankfully, all of these addresses do not contain null bytes or new line characters. Actually, no, that one doesn't contain new line either. So any of these addresses would actually work for us. So what I'm going to do is take that last EAX one. I'm going to shove this in a constant here. So call EAX address. Now what we want to do is we need to change our save return pointer overwrite address so that it points to the call EAX address. So we can use the pwnlib.pack32 function, which takes a 32-bit integer and packs it into a little endian ordered 4-byte value. So call EAX address. So hopefully, when we run this, control will be passed back to the beginning of our buffer. Now, beginning of our buffer at the moment contains a bunch of A's, which isn't particularly useful to us. We want to know whether we got there or not. So I'm going to change that to hexcc, which is int3, effectively the same thing as a software breakpoint. Okay. Do we have any questions so far? Everyone seems to have gone rather quiet. Sing out if you're stuck or if I'm not making sense. As I said, I'm trying to go through this a little bit quicker. Yes, Foob, this session is going to be recorded. It'll be shoved on YouTube. Alright, no questions so far. I will carry on. So we've got a bunch of breakpoints at the beginning of the payload. We've got our return address set so that call AEX is invoked. So from there, hopefully we should be able to see code control get passed directly back to our buffer that we've sent. Okay. Attach, continue, boom. Okay, so as we can see, control has been passed to a bunch of int3s. Int3s are hexcc. So we've passed in our payload that contains in a bunch of int3 instructions. It's overwritten EBP, as you can see, with a bunch of CCs. It's overwritten the save return pointer. Sorry, just laughing at some comments. The save return pointer is overwritten with the return address that points to this call EAX address, right? So then when the function returns, it returns directly to the call EAX instruction. And given that EAX pointed directly to the beginning of our buffer, it invoked our code, which is glorious. So all we need now is something a little more meaningful than a bunch of breakpoints. So let's go back to, where was it again? Exploit framework. Let's go back to master because I was playing around with payloads earlier on. So I'm going to go MSF Venom. We're going to have the payload of Linux. I think it's x86. What is it? Command exit? I should probably list the payloads. And grep. Sorry, I'm failing at the keyboard tonight. And grep Linux. No, list space payloads. You can tell I work with Metasploit a lot, can't you? Okay. Linux x86. All I want is exec. So there it is there. So let's go msf venom payload command equals bin sh. We're going to need to specify some bad characters because we don't want nulls and we don't want new lines. I'm even going to get rid of carriage returns just to make sure that they don't cause any problems. I'll manually set the encoder to x8, I think it's x86 Shikata Ganai. Format is going to be raw, so I actually want the raw bytes to come out, and I'm going to point that at something called stream. We'll call it, we'll just call it shell.bin. Yeah, Alex, I know they do, but I archive the videos on YouTube as well. So I'll put them on YouTube and they will stay there. Okay, so as you can see now, we've got our shell in binary form. So let's go back to the stream and we'll just go XSD shell. So as you can see, it's pretty small, but it's in binary format deliberately. Because if I go up here, what I'm going to do is I'm going to have shellcode set to read file of shell.bin. So we've read that completely into memory. I'm going to shove this at the start of the buffer. So that's where our shellcode is going to live. I'm going to change this back to A, but instead of leaving it at SRP offset, we need to make sure that we account for anything that's been added to the buffer so far. So we'll adjust that accordingly, and I'm going to put a single breakpoint. In fact, no, I'm not going to put any breakpoints in. I'm just going to fly by the seat of my pants. So we've got our shellcode at the start of the buffer. We have padding all the way up to the save return pointer. We then write the address of call AAX, and we should be done. Here we go. Yes, so 202, the reason why I'm using the encoder is because null bytes and new line characters are special cases for the getS function, and so getS keeps iterating until it finds something that it's not happy with. So new lines and nulls tend to make it stop reading, and so it will stop things from reading and writing over the end of our buffer on the stack. The reason why I chose that particular encoder is because I know it and it produces pretty small payloads. So that's why I chose Shikata Ganai. That's generally the default encoder when you use MSF anyway. And so, yeah, I do it explicitly so that you can see what's going on behind the scenes. So yeah, short answer is explicitly specifying the default because it's actually a good encoder that produces small payloads. All right, let's see what happens. Shell! Woohoo! So, as you can see, our shellcode has actually been executed, and we now have a fully interactive prompt with everything in it that we would expect. Okay? Easy mode. So, with that out of the way, yeah, I think a few people are expecting the dance too, Sean. But I'm going to save the dance for the end of the next one because the next one's actually quite substantially harder, and this is going to take quite a long time. Okay, so does anybody have any questions there about the standard baby's first stack buffer overflow save return pointer overwrite? If there are any questions, say them now, or forever hold your peace because we're about to get into something that's a little bit more exciting. I'm going to archive exploit off to, we'll call it I'm going to call it o1exploit.py, and the reason why is because I don't want it interfering with any tab completion of anything else that I'm currently doing. And I'm going to reuse the file that I've currently got open, and you'll see why very soon. But as I said, the file that we're going to be looking at now is pretty much exactly the same as what we've just looked at. The big difference being that NX is not enabled. So what I'm going to do is I'm going to take our exploit, I'm going to modify it so that it points at guessing 2. I'm going to run it again. Let's run exploit. We're going to attach, this time with GDB, we're going to attach to guessing 2, continue. Now what we should see is a nasty seg fault, right? So as you can see, we've ended up with a sig-seg-v, so we've seg-faulted because we're calling EAX. Now EAX points to the stack, but unfortunately, if we look at the VM map, you can see EAX is FF91CBBC, which lives in here. Right? Now the memory permissions on this area are read and writable only, so we're not allowed to execute code that's on the stack. So this is a problem. In fact, it's a big problem. As a result, none of the information that we're able to put in right now is going to help us. So we need to change tactics a little bit. So for those of you who aren't familiar, the general approach when it comes to bypassing NX is something called ROP, Return-Oriented Programming. Now as you'll see here, NX is enabled, so that's the only change. So what we now need to be able to do is come up with a way of modifying the program so that the data that we send it in some way gets executed without us actually being able to execute our code up front. Okay? So that's what ROP is all about. So for a real sort of layman's description of ROP for those who aren't yet familiar with it is this. If the stack and the heap, for example, are marked as non-executable, then none of the data that we've been able to pass to the application is going to be executed if we somehow manage to pass control, just like we've seen on screen. So the only things actually in memory at the moment that are marked as executable are existing code sections. So if we look up here, guessing 2's code section is marked as executable. libc marked as executable. LD marked as executable. VDSO executable. Now all of these things are effectively not in our control. We don't have the ability to influence these at this point. Part of the problem too is even if we did have the ability to abuse a stray pointer that pointed to some area that was executable, you'll also notice that every one of these is marked as readable and executable, but there's no read, write, and executable. So even if we had a write primitive that allowed us to point to an executable area of memory and try and write a value, it wouldn't work. We would end up with another seg fault because we would end up with an access violation because we're trying to write to an area of memory that's not writable. Okay? Now, if all we have in memory at the time that can be executed is code that comes with the application and the libraries that it depends on, that's the only code that we can actually execute at this time. So in order to abuse this bit of information, what we need to be able to do is find some way of executing bits of code that already exist in memory that will in some way help us try to change the way the application currently runs. Okay? So in Linux, this is one thing that's different to running in Windows. In Linux, a userland application can make syscalls, which basically says, I want to talk to the kernel, and I want the kernel to do a particular thing for me. In Windows land, we don't actually have that luxury. We have unfortunately we've got to rely on dependencies such as kernel 32 and NTDLL, and you have to look at the process environment block, and you've got to enumerate dependent DLLs, and you've got to search for entries in function lists and whatnot. But thankfully we don't have that pain here. We have the ability to invoke syscalls directly. Now, applications like this tend to invoke syscalls themselves. So one of the things that we tend to do is look for existing pieces of code that do things that we also want to be able to do. Now, one of the bits of painful stuff that we've got going on here is that this application is actually pretty small, and there's actually not a lot of code in the app that we can look to abuse, and I'll show you that in just a minute. But before I get into that, it's important to understand that there is one special register that is going to help us achieve what we're looking to achieve, and that register is the stack pointer. So if we look at the registers again just for a minute, you can see here, so we've got all of the typical 32-bit registers. The stack register, which points to the stack, is a special case when it comes to execution of code, because it keeps track of things like return addresses and various other things. So what we know is that values that are on the stack can be passed over into EIP so that they can be invoked. And we can do that by using the ret instruction. So if the stack is pointing to a particular value and a ret instruction is executed, then the value that's at the top of the stack gets copied into EIP, and then ESP is incremented by 4 bytes. So that has the same as popping or moving the stack ESP further down by 1 architecture-wide value, which on 32-bit is 4 bytes. So we could call ret and move the stack down. Okay, so if we called ret again, we would just keep moving ESP further and further and further down the stack. Now, every single time we call ret, we pop that value off the stack and it goes into EIP. So if we had the stack filled with addresses, and all those addresses just pointed to some other area of memory that had a ret in it, all we would see is effectively a NOP. We would see pop the value off the stack into EIP and ret. Same again, ret, same again, ret. So we would see ESP move down and down and down and down, and we would just see ret instructions being called, right? Now what I'd like to do is demonstrate that to you. I'm going to quickly jump back to Binary Ninja, and you'll see here this function here has a ret instruction at this address, so we're just going to copy this address. Go back to our exploit, and so I'm just going to call ret address is this, okay? Now for the sake of this exercise, I'm going to get rid of our shellcode for now because it's no longer relevant. We're going to have a bunch of A's that fills up our buffer right to the point that we were going to be at. But instead of call EAX address, what I'm going to do is have ret address. And I'm not just going to have it once, we're going to do it 10 times. Okay? So all I've done is I've changed our payload so that we've filled it up with A's, we've got to our save return pointer location, and we've specified the address of a ret somewhere in memory. Okay? And what I'm going to do is I'm going to set a breakpoint on that address so that we can see this in action. Okay? So let's do that. For those of you who are familiar with ROP, you might find this a little bit, this bit just a tiny bit tedious. But I think it's really important for people not familiar with ROP to visualize how ESP can move just by having certain addresses at certain locations. So let's run the exploit. We're going to attach. Now this time, instead of just attaching, we're going to take the address of ret and we're going to break on it. Okay. So we've set a breakpoint at that address, and just to show you that I'm not full of it, I'm going to go x10i that address, There you go, you can see it right there. That's where we've set our breakpoint. Okay? So that's where we would expect to see things stop. Alright, so we continue running our exploit. Now don't forget that this ret actually gets invoked once by the code before our code actually gets invoked. Because in order for our stack buffer overflow to be invoked with our save return pointer, the function has to return in the first place. Okay, so here we go. So if we take a look here, we can see, so I might make this full screen just for a sec. We can see here that EAX points to the start of our buffer like it did before, 144 times. EBP contains 4 A's, and then ESP, as you can see here, this is a stack visualization here. You can see that every single 4-byte block contains the same address, and that address points to ret, which is what we are currently looking at here. Okay, so if I step into this instruction, it'll look exactly the same, except for one small thing, right? ESP has changed, right? You'll notice here, ESP was 1C, now it's 2.0. So that means that when we executed ret, we popped that value off the stack, moved the ESP down to the next chunk, and did it again. Yeah, and did it again. So if we continue to do this, you'll notice, look at the top of the stack there. You see how the values, slowly we're moving down the stack. But we're still executing code, right? We are still executing, even though they're just single ret instructions, we are executing code inside the application under our control. It's not code that we've given the application, it's code that's inside the application, but we still have code execution here. We're still in control. We just are working within certain constraints. Now, if you can imagine, every single one of those addresses that I've specified there, they're all just ret instructions. But it's fair to assume that if we point our our address to something a little more useful, so long as it finishes with a ret, right? As long as it finishes with a ret, we know that we can continue to move ESP further down to other areas of code. And that's where it really starts to get interesting. Okay? So return-oriented programming is this in a nutshell. We need to take bits and pieces of code from memory that's already there, and we need to take the function prologues, I should say epilogues, among a bunch of others, and we need to look for snippets of code that are going to help us do things that we want to be able to do, right? Now, in my case, I want to execute a shell. I want to shell it somewhere, okay? But in order to do that, I need to find instructions that are going to help me sort of craft a call that will invoke a shell. Now, if we go back, before we continue, let's just go back over here. I've got a syscall reference link handy. I'm just going to paste that into the chat so you guys can have a look at that as well, because it is very handy. Better enable JavaScript. Now this thing gives you some information on Linux syscalls, at least in 32-bit, and tells you what is expected in certain registers for those syscalls to function. Now, when I was doing this the first time, this isn't the first time that I've looked into this thing, I was not aware of just how feature-rich pwnlib was, and there's something in pwnlib that makes this next step very, very easy. But I did it on hard mode, and as a result, you guys are going to do it on hard mode with me. So, that might suck, but you'll just have to deal with it. Now, so to begin with, we need to know what kind of code we want to execute, and we need to know whether the application that's being targeted has enough of these little snippets of code that are going to allow us to do various things. Hey Peleus, welcome. So guys, Peleus X, who's just mentioned that is here in the chat. He is the author of this binary, so give him a pat on the back. Thank God for Peleus. Praise Allah, or something. Right, so I am interested in sysexec. Now, sysexec, as you can see, expects some very interesting parameters. Now, the first parameter that it expects is I should quickly take a step back. Syscalls are invoked using a syscall instruction, and it relies on certain values being in certain registers in order to be invoked. Okay, so we don't pass things on the stack when we do a syscall, we pass them via registers. So when I first looked at this, I thought what I want to be able to do is construct a series of instructions that will result in the registers containing the appropriate values that I want, right? Unfortunately, proved to be a little harder than I had expected. So anyway, this was the path that I went down to begin with. I thought I need to construct a sysexec VE call. Now, at this point I thought, right, I'll go and have a look at what pieces of code exist inside the application that we can actually reuse. Now, what these little snippets of code are often referred to as are ROP gadgets. Okay, so if you've ever heard the term ROP gadget, what that means is looking through a piece of a binary or a library and finding anything that looks potentially usable that ends in a ret instruction of some kind, right? Okay, so I think is it ROPper? So I've got this tool called ROPper, which I've pulled off the internet. I didn't write this, and you'll see that ROPper. Oops, quit. It does a bunch of magic stuff. Now, let's just scroll back to the top here. So you can call ROPper, and you can pass it a file. And basically what you want to say is, hey ROPper, go and look at this file and give me some information on all of the ROP gadgets that live inside that file. And it tends to, you can also pass in the architecture. So what I'm going to do here is I'm going to say, ROPper, use x86, is it capital X? No, x86 architecture. And I want you to look at stream guessing 2. Okay, so this tells us here that we've got 96 gadgets. Okay, and as you can see based on the output, every single one of these results in either a call or a ret or a jump, something that passes control somewhere else. Okay, so as a fairly classic example, pop, and ret. So this means that this particular snippet of code will take a value at the top of the stack, pop it into EDI, move the stack down, take the next value, pop it into EVP, move the ESP down, and then ret. So for this particular instruction, we have the ability to set EDI, EVP, and before invoking our next gadget. Okay? So what I'm going to do is I'd like to just demonstrate this, just again for those people who haven't seen ROP in action before. I'm going to take this and I'm going to shove it in our exploit, and I'm going to explain just quickly how it works. Okay? So I like to go pop, yes, is it pop EDI, pop EVP ret address equals, so I selected the whole line there, didn't I? I don't need the whole line. Okay, so we've got that. Now what I'm going to do is quickly rerun this, and I'm going to redirect that output to stream ROP.text, so we're going to have to run it again. Go back to stream so that we're ready to attach when we need to. Now, I'm going to leave this as it was, okay, except we're going to have the ret in there before so that we can see the breakpoint, we can see where our code starts. And the next thing we're going to do is we're going to have the pop, oops, sorry about that, pop EDI, we're going to put that address in. Now, at that point, it's expecting a value to be put in EDI and a value to be put in EBP. So I'm just going to pick something not so random, equals CCCC. So this should go in EDI, and then DDDD should go in EBP. Okay? So I'm going to run this now because I want you to see this in action, just so that it becomes a little more clear. Okay, run the exploit, attach with GDB, should set that breakpoint again before continuing. Okay. Now, this is the first call to ret, so this is before our initial stack buffer overflow save return pointer invocation has happened. As you can see, our ret, which we put in as part of our first instruction here, is still sitting on the stack ready to be invoked. Okay? So if I step into this, right, we will end up exactly where we were before. The difference is that ESP has gone from 3DC to 3E0, and at the top of the stack is this new address that points to pop EDI. Okay? So when I invoke this, you'll see that control is now passed to this area where pop EDI is stored. And so what should happen is the first 4 bytes that are sitting on the stack should get popped into EDI. Now, as we can see here, the next 4 bytes are the 4 bytes we specified over here immediately after. So, looking at EDI right now, you can see EDI contains an address that looks like it's pointing somewhere into maybe the heap or something. If we invoke this instruction, EDI now contains the Cs that we specified. Okay? The first ret isn't needed. I left the first ret in there just so that you could see something familiar that we already covered before. So no, it wasn't needed at all. I just left it in there so that there was a level of familiarity. Okay, remember, what I'm aiming to do here is teach, not just exploit things as fast as possible. And I want people who aren't familiar with ROP to be able to see everything that we specify appear on the stack and get executed individually. Alright, so for those people who are asking, that's the reason why I'm doing it. But when we finish with our exploit, I won't be using that return address at all. I'm just doing it purely for illustration purposes. Okay, and you'll see that same ret address again in just a minute when we get to the bottom of this particular ROP chain. Okay, so we've popped our value into EDI, so we know EDI now contains CCCC. At the moment, EBP contains all the A's from our previous stack buffer overflow overwrite, but after this call, we'll see the D's appear. So there you go, EBP now contains the D's. Now the next instruction is ret, which was the end of our little gadget, and as you can see, we've lined it up perfectly. Our next thing is just yet another call to our ret address. So we can see the bounds in which we're working in, okay? So hopefully, you should be able to see that with these little snippets of code, we can execute like tiny operations on registers, we can move some data around while still actually having code execution. In this particular case, all I've done is influenced EDI and EBP, but that's something, right? That is something. So that is the general concept of ROP, is we use the sort of epilogue of all of these functions that we have available to us and craft values in registers that will allow us to invoke function calls. Okay, so now that's the easy bit. This is where it's going to start getting a bit more fun. So I'm going to quit out of this just for a minute, and I'm just going to look at the ROP gadgets. Whoa! It'd be really nice if it didn't do that with color, hey? Let's go back to ROPper and do ROPper Is there a way of avoiding color? I'm pretty sure there is. No color. There you go. So let's add the no color parameter. There we go. Okay, so that's a little bit more readable. So these are all of our gadgets, okay? Now, when invoking a syscall, the first thing that we need to do, like the syscall instruction itself, I believe, is int08. And so we need to be able to find a gadget that if we were able to do some kind of syscall, we would need an int08 instruction, okay? So, let's quickly search. Again, we're going to use Metasploit for this. Should probably leave these open in a separate window, shouldn't I? Let's do that. Let's leave that in stream. And we'll go to... We don't need binary ninja anymore, so I'm just going to quit out of that. Let's go Metasploit framework, tools, exploit, and I'm just going to run Metasm shell. So if we go syscall 0f05. Okay, so is that the same as int8? cd08. Right, so let's quickly look at our documentation. We should be able to go to, in fact, let's use the online disassembler. If you guys haven't used this is pretty cool. Just to validate what we're looking at. Online disassembler, I'm going to need JavaScript enabled. I've actually recently installed this anti-JavaScript plugin, which is why I'm having to slowly whitelist stuff. Google Analytics, no. Okay, so according to this, syscall is 0f05. 0f05. So that's definitely the syscall instruction. Whereas cd08 was int8. cd08, I should say. So int08. So what from memory, I can't remember exactly which one of these I used, but I'm pretty sure that either one of these should work. Okay, so either way, we need to find a syscall inside our ROP gadgets, our selection of code. So all of these gadgets here, as I said, they came out of ROPper. That's ROPper parsing the binary and saying these are all the things that look like they could be useful to you. But there's literally no syscalls in here. Okay, so that's a problem. Because for us to be able to muck with anything, we need to be able to do a syscall. So while I was working on this, I found myself in this little scenario. I'm thinking, okay, I need to be able to invoke a syscall, and I need to be able to do something fairly useful with the very small amount of ROP gadgets that I've currently got. But I don't have the ability at all to invoke a syscall using what I currently have. So this means I need to find one elsewhere, okay? The problem that we've got though is when we run the application, and I'm going to just do this directly with GDB, I'm guessing too. I'm just going to run, and then I'm going to break and look at the VM map. Now, you'll see what we've got here. I mean, our guessing binary is always in the same place. We can rely on the addresses inside guessing. Unfortunately though, we can't rely on things like libc because of system ASLR. So libc is going to be loaded into different areas of memory every time this application is invoked. So we can't even rely on the fact that libc will be there. We can't rely on libd being here. This poses a problem for us because if we were to throw ROPper at libc and say, hey, give us all the ROP gadgets in libc, it would come back with thousands of them. But if we don't have a base address that we can rely on, we have no way of determining exactly where in memory at any given time that instruction inside libc just happens to be. So in order to do that, we need to be able to leak some memory. We need to be able to read some memory out of the application. We need to be able to say, hey, give us some kind of address, give us a pointer, give us something that will allow us to extract data from the target system's memory. Remember, we're pretending to run this remotely, so that we know the base address of the target, so that we can then use sort of fairly typical offset calculations. Pelias is a cracker. Like, correct me if I'm wrong, when Pelias first created this binary, it was just the babies first. It was just a nasty idea after the fact to rebuild it with NX enabled so that it becomes a lot harder. Okay, so what I did at this point is I thought, okay, if I don't have any syscalls, I need to be able to find one on the fly. I also continued to look at the options that were in the syscall list. And I thought, well, sysexec actually, it requires quite an excessive combination of parameters. And given that there is a very limited number of ROP gadgets available in the current binary, we're going to need to do something smarter. So I decided instead, would it be worth us changing the memory protections of the stack on the fly and then execute the code that's on the stack? Okay, so I started investigating other ones, and msysprot turns out to be a much more fantastically viable option. So when you call memprotect in C, or mprotect I should say, it effectively maps back down to this sysmprotect syscall. And what it does is it says, I want you to change, I want the kernel to change the permissions on this section of memory to something completely different. Okay, so you'll see here, EAX needs to be set to 7D. 7D says when I run the syscall, I want the mprotect syscall to be run. EBX needs to contain an address. So EBX needs to point to the area of memory that we want to change our memory permissions on. Okay, so for us, that would be the stack. We would want to be able to change memory permissions on the stack so that when our syscall returns, we could jump back to where we are on the stack and literally execute code that's sitting on the stack. Thirdly, ECX needs to specify a length. Now that length, I think it needs to be, I don't think it needs to be page aligned. The thing with, here's one difference actually that's interesting between Windows and Linux. The equivalent in Windows is a function called virtual protect. And with virtual protect, you can pass a pointer to anywhere in memory and it will go, oh, even if you're halfway through a memory page, it knows that you want to mark that memory page completely and it doesn't fail. Unfortunately in Linux, if you specify an address that isn't page aligned, it will crash. So yeah, we're in a world of hurt here in Linux insofar as if we're going to pass a pointer to the stack, we need to make sure that we actually page align that pointer before we do any magic with it. Okay. So then we need a length. Now for us, that's a pretty simple thing. We literally only need something non-zero. Okay, non-zero is fine because you can't mark anything less than a single page as writable, readable, or you can't change the permissions of anything less than a page. It has to be a whole page or more than one page. So if we can have a non-zero value in ECX, we know that we're going to be good. EDX, again, changes slightly because we need to be able to say, I want to change the memory permissions so that it is no longer just readable and writable, but we want it to be readable, writable, and executable. Okay? So this is where it starts to get a little bit more fun. What we're going to do to begin with, before I go through the pain of locating a syscall, we're actually going to construct a ROP chain that will set up the values in EAX, EBX, ECX, and EDX so that when we know how to find the syscall, all of that stuff will sort of be ready to go. Okay, so going back to our main screen, let's quit out of this and let's go back to our ROP gadgets. Now I might just move this over a little bit. Welcome, Jardeth. Thanks for coming along, mates. How many people we got looking? Oh, there's a few of you. Nice. Alright, so far, is there anything about ROP or the approach that we're looking to take that isn't making any sense? If not, like, post your question now and I'm happy to answer it. Otherwise, I'll go through, and obviously as I'm constructing this ROP chain, I'm going to show you the steps that I'm taking and how that ROP gadget thing actually works. Question. So we can't use sysexecve because we've not got a ROP gadget like to execute, right? So how can we execute the and protect one now if we still haven't? Okay, that's a good question. I clearly didn't make myself clear. Okay, so we still do not have the ability to execute any syscalls whatsoever. The reason why I decided to move off sysexecve and go over to mprotect is not because we don't have a syscall gadget. It's because construction of an execve call using the very small selection of gadgets that we have available is going to be much harder. So instead, I decided let's go with just changing memory permissions and working with the smaller subset, because that will mean that we don't have to worry so much about pointers and getting strings written to areas of memory and null terminating them, and then having other pointers point to those pointers so that we can construct things correctly. Instead, a single syscall that will allow us to change memory permissions, and those registers just require simple values plus a stack pointer, is a lot simpler. So that was the thought process that I went through back then. I thought execve looks pretty hard given our limited ROP chain, our ROP gadgets, and so let's look at just using an mprotect call. Okay, so we need to be able to do some stuff. Now, actually, before we continue, what I'm going to do here is this. I'm going to change our exploit so that we put in a hard-coded 0 as our return address, and I'm going to show you why. Let's run our exploit. Let's attach using GDB, continue, run. Okay. Now here's the reason why I did this, to demonstrate that thankfully getS does only care about new lines, and that the value of 0 has been written to EIP. So that does mean that we can actually pass strings in memory quite nicely, and we shouldn't have any concerns with null termination as long as we avoid new line characters. That helps us immensely when it comes to construction of a ROP chain that's populating registers with values that contain 0. Okay? So let's go back here, for example. We know that we want to be able to set the value in EAX to 7D. Okay? So the first thing we need to do is go, is there a gadget that allows us to pop a value into EAX and then return? That's what we're looking for. And the reason we're interested in that is because we know we can pop values off the stack and have them written to registers. So let's go back to our spare screen, wherever that was. 3, 5, here we go. I'll create another one here. Screen, and we'll vim ROP text in here. I may have accidentally specified another one, but that's no biggie. Okay, so what we're looking for is a pop EAX. There's no pop EAX in here. That's a bit of a fizzer. Do we have the ability to move into EAX? Yes, we do, but we've only got a couple. That's a bit of a shame too. Can we exchange? There's no exchange calls whatsoever. This is looking pretty grim already, isn't it? What can we do with the AX? Let's see, we can call it. We can move null into it. That's not particularly useful. We can push it, we can call it, we can push it. We can test it. We can move 0 into it again, and that's it. So we literally don't have the ability to easily write the value of 7D into EAX. So we're already in a world of hurt. That's really not cool. We'll skip that for now, and we'll move on to other areas of the ROP chain. All right, so just give me a second. I have people pinging me. Okay. Right. Rightio. So, where was I at? So we want to be able to construct some kind of chain that's going to massage registers and have them do something sensible for us, right? In order to utilize that particular approach, being able to set a value in EAX is key. But as you can see, at the point of the crash, EAX points to the stack, and the ROP gadgets that we have don't allow for us to modify EAX. So that's a problem, and I can't remember how I got around it last time. Ah, here we go. That's how I did it last time. Okay, so if you can see on screen, what I've got highlighted here is a pop AL. Now this is super helpful, super helpful. Pop AL, in fact, let me take you to some documentation on this. Pop AL. That's not what I'm looking for. Pop AL ASM. So, assembly language tutorial, let's open that one. Pop AL. Here we go. Maybe this one will be more useful. Here we go. Pop all of the general registers off the stack. Okay, so that means every single register can be popped into. Yes, it's Merrick's Pop AL. Woohoo! So that means we can literally drop every value into every register in one foul swoop. Okay? So here you can see what it's saying here is you can pop all of the general registers. Pop AL says pop EDI, then ESI, then EDP, then ESP, EDX, ECX, then EAX. Alright? So we're going to copy this for documentation. Jump back over here. I'm going to put it up here so we can see. Actually, let's put it down here. Pop AL. What was it? CLD ret. CLD ret. Address. Yes, I'm a bit of a stickler for variables. I like to know what instructions rather than just having a bunch of arbitrary packs throughout my payload. Okay, so pop EDI, ESI, EBP, ESP, EDX, ECX, EAX, ret. So what we could also do is go pop EAX, sorry, just to make it more descriptive. EDI, ESI, EBP, ESP, EDX, ECX, EAX, ret. Okay. It's very descriptive, okay? Very descriptive. That's the goal. So instead of our return, I'm going to go, oops, I did the wrong thing there. There we go. I'm literally going to pop everything off the stack. So EDI and ESI, I don't think they actually need to contain anything particularly useful to us at this point, right? So let's go back to the documentation and see what the syscall reference says. So EDI and ESI can be null. We literally don't care, okay? EDX needs to be the memory protection constant, okay? So we go back here. We go, so this is going to be, we're going to pwn.p32 0. So that's EDI. The next one we're going to do the same, that's ESI. Next one we're going to do the same, that's EDP. Now ESP, that's a concern, isn't it? Assuming that that's what the documentation said. It did, didn't it? Yeah, pop ESP. So, what's interesting about this is that all of a sudden, the stuff that we have on the stack is no longer reliable. We'll see why in just a minute. So we'll go EBP, ESP. I'm going to set ESP to something known. Now immediately after ESP, we have EDX. So what was EDX again? EDX needs to be, in fact I should probably take the documentation for, excuse me, the syscall. EDX is the memory protection, ECX is the length. So mprot EAX equals hex 7D, right? ECX equals length, EDX equals protection, which means EBX has to be a pointer, right? Easy. Alright, so everyone's still with me? Yeah. So we can't use that. Yep, these are on, and all this is below. Yep, okay, cool. Everyone's still on the same page as me? I know I'm flapping about a little bit here, but hopefully it'll make sense. So ESP we've now popped. We're next doing EDX. So EDX is the memory protection constants. Now what the hell do they need to be? Let's go back to a browser. And let's look at the documentation for mprotect. So hopefully that'll give us some information, because I can never remember these off the top of my head. Here we go. So prot read, prot write, and prot exec. Now what I do when I'm looking for things like this is I go hash define, I just go define and give it a constant, and somewhere we'll end up with with source code to what these things mean. Here we go. Read, write, exec. So in order for each one of these things to be set in total, we need to add them all together. So to get read, write, and exec, the memory protection constant we need is the number 7. I hope that made sense. Okay, so here we need to pwn back 32 the value of 7. So this is mprotect. Prot read, prot write, prot exec. Okay, and we know that goes into EDX. Okay, so ECX I believe is next. Yep, ECX. Oh, I missed. It looks like I've missed EBX out of that. EBP, ESP, EDX, ECX, EAX. Yeah, it looks like EBX is actually missed from that list for some reason, but we'll come back to that anyway. So ECX needs to contain the length, so as long as that's non-zero, that's fine. But what I'm going to do in this particular case is I'm going to, thanks for pointing that out, Smiriax. I just accidentally left the .p32 on there. Yeah, it's definitely an error, so I've got rid of that. ECX needs to be at least 1, but I'm actually going to get it to memory protect more than a single page. Pelias is trolling me. So what I want to do is actually, rather than specify a single page, I'm going to specify 2 2 pages of memory that I wanted to overwrite. And the reason why I want to change memory permissions for 2 pages is because if for some reason the area of memory that we're changing the permissions on happens to go across a memory page, I don't want it to crash in that particular case. So we're going to do 2 pages. Okay, ECX, then after ECX we have EAX, which we know needs to be, just put size length into ECX, and then EAX contains syscall for and protect. X7D, was it? Syscall reference 7D. Okay, so I'm going to go ahead and run this. Yeah, if you can specify 2, I would recommend it, because usually what you end up with is, particularly if you're modifying the content of, the memory pages of the stack could be more than 1 page in size. So I usually specify 2. The reason why I only specify 2 is because when we finally get code execution, the amount of data that we actually need to write to memory and sort of bootstrap a shell or bootstrap an interpreter payload tends not to be that big. So you don't need, like, remember a page is 4K, right? So if we specify 8K, that's more than enough space for us owning stuff and to bootstrap a better payload. We don't actually need to go further than that. So that's why if I have control, I go with 2 pages rather than more. If you specify more pages than that, then you run the potential of marking memory pages beyond what's currently allocated, currently mapped to the process space, and attempting to change memory permissions on something that isn't valid, and you'll end up with a crash of a different kind. So we may actually come back to this and go, you know, I'm not even going to do 2 pages, I'll only do 1, because we may have already gone too far. Alright, so what I want to do is run this. And I want to see what it does, because I think something's missing. So, run the exploit, attach, set the breakpoint, come on, continue, go. Alright, so, here we go. So let's have a look at what our current mini ROP chain looks like. You can see that we've landed on the ret, which we know is going to get invoked because our function is about to return. Looking at the stack, we can see that the pop A instruction is going to be executed, which is awesome, followed by all the other values that we've hard-coded. Okay, so let's do some simple steps and we'll see what happens. Alright, so pop A, look at the stack carefully and look at the state of the registers. Okay, all of these registers. Now I'm guessing EBX is missing out of that list for some reason, so we might have to add it ourselves, but hopefully we'll know based on the values that we're seeing. Okay, so let's step. Boom. Alright, so the documentation is clearly wrong. EBX is 7, and that's what we thought was ECX. Okay, so what we might do is go in sort of a kind of a reverse order. These 3 look valid, right? ESP is untouched. Now that's interesting, isn't it? ESP at this point is untouched. That's actually a relief. But CCC appears nowhere. You see that? So that value is clearly ignored. So that's great. That means that ESP stays where it should be, and nothing breaks. Okay, so this here is the memory protection constant, and that should go into EDX, but it's gone into EBX. Okay, EDX currently contains what ECX should contain, and ECX should contain what EAX contains, and EAX contains the ret. So basically, the issue that we've got here is that EBX, which should contain a pointer, and this is where it's going to get tricky. The pointer that we are looking to change the memory permissions on. So let's set this to just an arbitrary value, pointer for mprop call to change. Okay, so let's run this again. Great, continue, boom. Okay, so here we go. Watch the registers now. EAX contains 7D, exactly what we need. So that's our syscall identifier. ECX is 2 pages worth. EDX says change it to read, write, executable. ESI, EDI, EVP, currently we don't care about that at all. So the docs, thanks Peleus, the docs says it skips ESP, so that's awesome. EBX, this is the register that's going to cause us some hiccups, right? Because EBX needs to point to something meaningful. But as a result of doing what we're doing, we've actually smashed all of the registers and got rid of pretty much every interesting value that we're looking for except for ESP. So what are we going to do? We need to be able to mark an area of memory as read, write, and exec. However, in order to make use of such a thing, we need to be able to write to that area of memory that's going to contain code. Now, for us to be able to do that, we need to have a fairly constant address. So if we're looking to do this, then we may actually be in a bit of a world of hurt, because we're going to be losing our pointers to things that we know while we're actually trying to change the memory protection of the area of memory that contains the code that we're looking to execute. So that poses an interesting problem for us, right? What we ultimately want to do is go, I know that there's data here that I control, and that data is going to be in a location that I can either predict or that I can maintain a pointer to along the way. So the problem we've got here is we don't have the ability to do both of those things. What we need to be able to do is say, okay, we need to write data to memory, and we need to rely on the location of that area of memory so that we can change the memory protections of it and jump to it at the same time. So this is where it really kind of turned a little bit of a corner for me, because I can't use a pop-al instruction to populate all of my registers, and from there sort of return control to something that I know exists, because we don't have those pointers anymore. But what we can do is we can look for another area of memory, something that is constant, something that is readable and writable, something that's inside the memory area and mapped to the same location each time the binary is run, and maybe we can do something with that. So, as I said, before I look at the VM map, the fact that we can't protect something that is on the stack because of the means in which we're using to make the syscall is a problem, because we don't know where the stack currently is thanks to ASLR. So this payload that we've got here at the moment is effectively useless to us. We need to find a way of marking a constant area of memory as read, writable, executable, and have our data stored in that location. So let's look at our virtual memory map. What we're looking for is an area of memory that we know is going to be in the same spot. Now, looking here, you should be able to see that this section of memory immediately after the text section is interesting to us. Why is this area of memory interesting to us? Well, if we disassemble this a bit, let's have a look at, have a look at this data that's in memory. There's really kind of not much that's very descriptive at all about this. This looks like memory that is effectively used for global variables, right? Global variables, obviously, we need to be able to read and we need to be able to write. So perhaps what we can do is somehow abuse the fact that this memory address doesn't change, And instead of marking this area of the stack as read-write exec, we could mark this area as read-write exec. Obviously, there's a problem here because we need to know that we can somehow write to this area of memory in the first place. Well, the good thing is that we can. Let's have a look. Oops, sorry, I've done the wrong thing there. We're going to go info functions. No, I don't. I want to see the GOT. Where's the GOT? How do I get to the GOT? Better help. Is there a show me the GOT function in PET? I can never remember. If you guys know off the top of your head how you browse the GOT really easily, then let me know. Otherwise, I'll probably just fire up Binger again. Reopen, and then we'll go to Win, which uses this, and we'll see here. Okay, so global offset table was probably before, right? Here we go. So everything after this, we're getting back down now to the memory area. This stuff here, 49000. So this area of memory here, right, is interesting. Correct me if I'm wrong. Let me just quickly duck back here. $49,000. So this is the area of memory. As we can see, like there's a big area that kind of effectively contains nothing. But it continues on, and here's where we can see, here we go, here's the global offset table. Right, so I have covered off what the global offset table is in a previous stream, but I didn't record that stream because I was a Twitch noob. But what I think we can do here is we can abuse the fact that we have access to getS. Oops. We have access to getS here. GetS points to a function that will read in a chunk of data. So perhaps what we have the ability to do here is this. We could say, create a ROP chain that writes generates a call to getS, and the call to getS actually points to that address further up here, so somewhere in here. Okay? And from there, we could write our payload to memory at this location, or some other location in this area of memory, using that getS call. And once that's written to memory, we could then say, hey, let's somehow, we'll mark that area of memory as read-writable executable, and then we can literally jump to that location in memory fairly easily. Okay? So what I'm thinking is we'll construct a mini ROP chain that invokes getS, and we'll point it to somewhere within this memory region, and we're going to write our shellcode to it. Okay? So let's do that. Move this over a little bit. Is that making sense, or are people going to need to see what I'm talking about before this actually happens? I would assume the latter. What I should do is get the GOT entry for this before we do anything else, because I missed it. So the GOT entry for getS is here. What's also interesting, is probably worth noting, is we have the ability to put S as well. If we have the ability to put S, we have the ability to disclose the contents of memory. Hooray! This is important. The reason why this is important is because, well, two reasons. One is we might want to get stack addresses, heap addresses, that kind of stuff for other functions. But we know right now that we don't have the ability to execute a syscall because we don't know where in memory a syscall instruction happens to be. So we could probably use putS to determine that, which is awesome. Okay? So I'm going to steal these two addresses, address for getS and address for putS. Copy address. Now I'm going to put these as got getS address equals, and putS will be something else. Alright, so they're the two areas that contain getS and putS. Right, let's go back to the beginning of our ROP chain. For now, I'm going to comment out everything that we've done so far, but I'm not going to throw it away. Now what I want to do is we want to return to getS, which is going to ask us for more info. Okay? So buff plus equals clone.p32 got getS address. So when we return to getS, it's going to expect something interesting. First of all, it's going to, the stack actually needs to be laid out in such a way that looks like a fake stack frame. Okay? So when you make a call, remember, you say, you push an argument, you push an argument, you push an argument, you push the return address, and then you push the function that you're calling. You then invoke the function you're calling. So if you picture that in your head, you should see directly underneath where the current stack pointer is, we should see the return address, followed by all of the function's arguments. Now we're only passing one argument in, okay? And it's going to be this address here. Okay, so I'm going to change this and put this up here. So I'm going to call this payload address because we're going to store the payload in this address eventually. Okay, so the first argument is payload address. And then immediately above that, one argument, remember getS takes a single argument, immediately above that we need the return address. So that means the address of the gadget that's going to be executed immediately afterwards. Now also, bear in mind that we're using what I believe to be is effectively a standard call approach, or I should say a CDECL approach, which means the calling convention says that the caller has to clean up the stack, not the callee. That means that whatever it is that we return to, it needs to skip over the top of this address so that it doesn't actually get used as a return. Okay, so that means we're going to have to look at some ROP gadgets. We need to find something that basically pops that value off the stack and then returns so that we can effectively throw it away. So what we're looking for is something that starts with a pop into any register, so E question whatever, followed by a ret. What did I do wrong? So we're looking for pop E something something ret. I'm failing at regex clearly. Something something should be dot dot. There we go. Okay, so look, we've got a couple of options here. There are two gadgets here, one that says pop EBP, one that says pop EBX. Now we know that EBP is not particularly interesting to us ever, so what I'm going to do is I'm going to store this gadget up here. We'll go pop EBP ret address. Okay, so what we want to do, and this is going to be a little bit confusing if you haven't seen it before, is we set our return address to pop EBP ret. So that means that when we return from the getS call, this gets invoked and we skip over this before going back to whatever this will be. I like to set it back to the, what is it, ret. It's just a plain old ret, isn't it? Ret address. Okay. So let's step through this so that you guys can see how it works. Something else to bear in mind. When our payload's sent down the neck of this thing and it gets invoked, it's going to call getS again, and that's then expecting to read some stuff. So once we've sent our buffer here, we need to send the next bit. So let's do this. Let's just send it a bunch of Ds, followed by a new line to make getS happy. Okay, so this is the first payload. When the payload gets executed, what happens? Well, it calls, hey, give me some more stuff to write to memory. So this is what this bit does. Okay, let's see it in action. Change the window size again so that we can see it. Run. Attach, set that breakpoint again wherever it is, continue. Okay, bear with me, here we go. So we step into this one, and the first thing that happens is we end up, where are we? We are at A30. Why is this a problem? I know why this is a problem. The problem we've got here is that we've returned, I think, we've returned to the GOT, we haven't returned to the program linkage table entry. So we actually need to dereference what's in the GOT. So if we looked at, for example, whatever EIP currently points at, that's the address of the function that we're actually interested in calling. So this means we're going to have to change our tact a little bit. Going back to Binger, somewhere in here we'll see it, right? We will see a call to put S somewhere in here, right? So let's go back here and when we click on here, you can see like there's a cross-ref here. And this is, of course it is, that's a cross-ref to the reference to the PLT, which isn't really going to help us at this point. So what we should do instead is go to, is it win? Here we go. You've guessed correctly. And then it calls put S for us. So that's what we're looking for, is to go instead to this. The problem that we've got, though, is that immediately after that, it's going to do all of this stuff again. Well, is that bad? Not really. It's not really that bad, because thankfully we're at the tail end of this, and we have the ability to, for one, call put S and say cough up some data. And here, this getS, this is the kicker, right? This is the one, actually, I was wrong. This is the one we're actually interested in, not put S, we're interested in getS. So we can return instead to this, right? We can return to this, and this will invoke things for us. It will return back to this line here, which effectively moves stuff on the stack for us, so we will have to adjust for that. And then we'll end up with a not, leave, and a ret. Now this leave is going to pose us a problem, which you'll see in just a minute. So, needless to say, while I was going through this, I jumped all over the place and I changed my tact constantly, because the gadgets that we have available here are so weak that it's not really very easy to make good use of it. So let's take this call getS address, copy it, and what we're going to do is we'll store call puts address. Okay. Now, So we need to change this to call puts. Sorry, not puts. Gets. Okay, call the gets. We should have already pushed the return value onto the stack. Sorry, not the return value, the target buffer, which is the payload address. And then after that, there will be a call, as we saw back here. Once it comes back, it says add ESP, which pushes the stack further down by 16 bytes. So that's four values that we don't care about. So that is 16 bytes of junk. So this buffer for the add ESP 10. Now I'm going to leave this in here even though this isn't going to help us, right? Oh, hey Justin. Thanks for coming along, mate. Guys, if anyone out there doesn't know Justin, he streams some hacking stuff as well, and you should totally follow him because he's great. Partner in crime. Okay, so let's just have a look at what this does, because I think it'll behave in a way that you're not necessarily expecting. Can I do, is it, I think it's E. I'm going to put that breakpoint back in. Is it E? I think it's E. Yep, that's what it is. Okay, that means I should be able to do E. Continue. No? What's going on here? I'm not doing something correct. Is it X? No. C? Ah, bugger it. Let's just do a manual like we did before. I'll come back to that later. Okay, so continue. Right, so what happens now? Let's have a look. When we step into this, we end up with a call to getS. Now, here you can see it's actually pushed a buffer onto the stack, and our buffer is pointing to that area of memory that contains what looks to be global variables, right? So let's go 16.x. So that's what the memory currently contains. I'm going to jump over that call and then have another look, and you'll see, look at that. It's got a bunch of crap in it, but we sent it. So all of these Ds now currently live in that area of memory. So that's awesome. So we have the ability now to write our shellcode to memory. Winning. That's really good. Here's where the problem starts. So add ESP. Look at the stack here. So add ESP 16. So when we step over this, you can see not leave, and when we execute leave, it breaks. Why is that? The reason for that is because leave, remember, is a synonym for two things. It does a move EBP ESP and then pop EBP. Now this is really bad because EBP is a value that we've overwritten in the past. So, yeah. So what happens here is that our stack is literally moving somewhere else. And this is not a good thing. Okay? So the fact that the stack has moved means that we now need to do something smarter. And this is where I thought, okay, we have the ability now to read and write data. We can use putS and we can use getS. The problem that we've got is we can't rely on the stack location anymore, which means that we are now going to have to instead pivot off an area of memory that we know is consistent. All right, so this is where it actually got painful. So before we go down this track, what I want to sort of highlight is that in order to continue, we need to be able to find a syscall instruction that we can utilize when we finally get to the point where we can do a pop-al a syscall ret. We need to be able to find that syscall instruction, and we also need to find an area of memory. So up until now it was all okay. No, it wasn't all okay. We were just working through the scenario and figuring out what was feasible and what's not. So what we've determined here is that we can store a payload in memory, but in order to utilize the gadget that we've currently got in order to read more information in, we lose our current stack. Which means now we're going to have to... No, it's not painful yet. It's not painful yet, trust me. What we need to be able to do is write to an area of memory and use that same area of memory for another series of ROP gadgets. So what I'm going to do is, we've got that area of memory that we know that we can read and write to, and I'm going to break it up into 3 chunks. The first chunk we're going to store our payload in. The second 2 chunks are going to be 2 different ROP gadget chunks. So imagine this. When our first ROP gadget executes, the first thing that's going to do is it's going to call getS to read in more data. That getS call is going to point to a chunk of memory that is going to store a ROP chain of some kind. Okay? From there, we're going to return to that and execute that ROP chain. Once that ROP chain's executed, we're going to run some code that will write some data to another area of memory, which again contains another ROP chain. And the reason why we're doing this is because we need to be able to, on the fly, generate ROP. We need to be able to, on the fly, read memory from the target. And we need to be able to, on the fly, write data to a completely different location in memory. And eventually jump to it once we've executed the syscall instruction. So, this is where it's about to get hard. Okay? This is where we're finally going on hard mode. There's an easier way of doing this, but this is hard mode. Right, so let's go back to Binary Ninja. I'm going to start moving a little bit quicker because it's 20 to 10 and we have a fair bit to get through. Okay, so what we want to be able to do is, at the time of the crash, we want to be able to say what area of memory contains some pointer to something that's useful. Okay? So, as you can see, we're at the point of the crash now, or I should not, sorry, we're not at the point of the crash now. Let's do that again. Right, set a breakpoint, continue. Okay, so this is where we're at the point of the crash. What we want to be able to say is there anything in memory right now that points to something useful, something that we know that we can rely on? Okay, so what we're looking for inside our virtual memory map is a pointer to somewhere, say, inside libc. Because somewhere inside libc, there is going to be a sequence of instructions that we need. And those sequence of instructions are CD08, and what's ret again? Ret is C3. So going back to C3, CD08 C3. I thought it was C3. Let's go over to Metasm. Ask Metasm. It is C3. So online disassembler is being a pain in the butt. What we're looking for is an int8 C3. So we need to be able to search through an area of memory looking for the sequence of bytes that are executable that map to CD08 C3. Okay, so we're looking for those three characters side by side. Now, the best thing for us to do, I mean, you'll notice here this VDSO contains code as well, right? We should be able to use search mem, which says give us a pattern, a start and an end. So what we're going to do is we're going to search for memory. Let's just see if this works. Is it CD08 inside VDSO? Oh, do I have to care about endian? Probably do. Or do I? No? CD is also red, huh? So for example, let's just disassemble that for a minute. Yeah, so ret is the same as C3. So why is it that I just said give me CD and it returned C3? Clearly I don't know how to use search properly. Search for pattern in memory. Is there another one? There's ref search, there's no find. I could have sworn it was search mem. ROP search mem. It is search mem. Can't remember what I'm doing wrong here, but there is something. There is substring string show shellcode. That's correct. So should search mem. Yeah. Sorry, I'm just I'm doing my current flapping about, trying to remember how I did this before. Support regex. Aha! There we go. That was me getting it wrong. So let's just quickly look at this. XBX. Yeah, there we go. Let's look at 16 bytes. CD0890. Okay. So if we were able to do a similar search for CD maybe it's no. Is this frustrating, guys? I hope so. Pattern search, search C3. Pattern search. No, pattern search is searching for cyclic patterns, right? I would have thought that search mem is a better option. Pattern search. Yeah, so I don't think you can specify anything interesting in there. It's definitely search mem. So let's go back to that search mem thing that I did before. Okay, so there's a few of them there, right? One of these has got to have a ret after it. So let's do that. x. We actually only need a few bytes past it. Why am I doing it that way when I should actually do for I? So there you go, there's an int 8. But pop, pop, pop. Whoa, there's one. Okay, so this is something that's doable, right? There's an int 8. Oh no, it's int 80, not int 08. That's not helpful. Alright, just give me a sec. I'm going to look something up. Okay, let me just make sure that I am doing something sensible. Yeah, int 80. So it's not int 08, it is int 80. So I'm looking for int 80 ret. And that's probably why I'm not having any like finding stuff. Right, there we go. And then followed by C3. Okay. Whereas that one there would be C085D. Let's see if this still works. Okay, okay. I finally understand what search mem does now. So this is what I would have done before. So we're looking for an int 80 call followed by C3. And let's see if we can do it in what's it, C? Let's try this one. Oh, come on, that's rubbish. Okay, there we go. There's a couple in LD, which is interesting. What am I doing? X. Okay, so there you go. This is effectively the thing that we're looking for. We're looking for an int 80 ret. Up here in VDSO, there's an int 80 followed by a few pops and a ret. Now, those pops are effectively harmless for us. We don't really care about those. But finding them might prove to be tough. Technically, we should be doing something else. So, what I did originally, I'm just checking back with what I did before to make sure that I'm not going too off base, is we start by going, and we're going straight to getS, pointing at the data section. Oh, that's right, and then we continue on. Of course we do. Okay. That's right, our ROP gadget is effectively not over at this point. So we have the ability to call getS and populate a payload somewhere in memory. 48420, is that where it was? Bear with me a second. Right. Aha. There it is. That's what I was looking for before. Clearly I failed to find this before, so we can actually invoke a getS call here by referencing directly into the what's it called, the PLT. Wow, I should have done this before. Okay, just to recap, I was originally going back to a call instruction which was completely destroying the stack and doing all kinds of horrible things as we saw, whereas here we don't actually have to jump to the call in that area of code. We can literally return to this getS, which does a direct sort of dereference jump into the target that we're looking for. So, huzzah! We don't have to worry about that to the extent that I thought. So, we can now have a jump getS address, okay? And that jump getS will have all the stuff in it that we knew we were going to have before. So we can get rid of that. We can leave that thing in. We can have the jump, and we can change this so that inside here we have the pop EBP ret address. So again, we're now simulating a call directly by dereferencing through the PLT, and that call will expect the next address to be the return address, which is what we're using to pop, and then immediately following that there'll be the payload, the address that we're actually writing to memory. Okay, so that's a bit more sane. Well, I was going bonkers for a minute there. Let's run this again. Any questions? I'm sure it's clear as mud by now. Break, where's my breakpoint? What did I just do? And I'm still going to need that. Run that again. Attach. Set the breakpoint. Continue. Program terminated with signal seek kill. Okay, so it's still not running. What am I doing that's stupid? Someone point me at my stupidity. Oh, hang on. Yeah, that's me being a retard. I need to set the yeah. Thanks. Hopeless, mate. Bloody hopeless. 8420. Isn't it amazing how, you sit down at a time like this and you know that there are a bunch of people watching you and even the very basics fail you. Look at the error in the Python script, OJ, you moron. Phew. Crazy. Alright. Let's attach. Let's set a breakpoint. Let's continue. Alright, so here we are. Sorry, we're back at it. We're back at it. We're back in business. Apologies for me being stupid. Okay, so let's quickly step into this. First thing we do is we invoke getS at the PLT, and that actually runs off and invokes the getS call itself. I'm going to step over that rather than... bastard. That's one thing that's annoying about the PLT is that it has to go through all of this junk. And I don't trust it to run to ret either by doing... what's it called? What is the thing to run to the next return? Step out? Step until. Step until the next call, step until the next jump. What's the next ret? Guys, anyone know? Run until the next ret? No, I don't think this is going to be helping anyway. Search min, snapshot start, step until. No. What I should do, here we go. Ret. pop EVP. So pop EVP, sorry I skipped over that. EVP is this address here, which now contains, this is the pointer to the area of memory that we just wrote everything to, so it now contains all of the data that we've written to it. Okay, so now we're actually back on track. We have the ability now to write a payload to memory. We have the ability to write to different parts of memory. Using the same technique, we can actually read data from memory as well. Finish. Thank you, Justin. Sorry, man, the lag plus me being distracted. Never help. I'm guessing that's not a PETA thing. That must be a what's it called? GDB. Could be just a GDB thing. So I'm looking in PETA help, but it's probably straight in GDB. Okay, so right, what do we do? Right, just print a string to the data section. Yeah, so what I'm going to do now is, given that we have the ability to write data, we know that we can write data to memory. What we need to be able to do is we need to find the instructions that we're looking for in memory that are going to give us the ability to execute a syscall. So in order to do that, there are a few ways. We can use, we can use Komputerz to print strings. We can use printf to print strings. If we use Komputerz, we have to assume that we're giving things valid pointers. Whereas with printf, we can use the sort of format string style %x, dumping hex off the stack. Previously what I did was, what did I do? Let me just have a quick look at my reference. Printf string to the data section. Yeah, so I used printf, and what I did was, where are we? Yeah. The stack to it. Yeah, okay, so I wrote a printf, and the printf string contained a format string that dumped a particular value off the stack, which led us to the base of VDSO. So that means at the time of the crash, let's see. Right, so we're going to write a value straight up at that location, at that point there. So we need to be able to do, yeah, okay. Now I'm not making any sense at all. Quit, run again. Attach, break. I'm going to show you the analysis that I did before. So at the point of the crash, what I'm interested in looking at is there anything on the stack that points to somewhere inside these other areas of memory that contain code? And what I found, rather than walking you through the painful process that I followed to get, and I'm just going to explain it briefly, is I found that 64 and 120. Okay, so the current position on the stack, we're going to look at plus, so we've got the current point of the stack, and I'm going to offset from the stack and dereference it. Okay. So what I did while I was trying to find interesting things inside memory, what I was trying to do was find something on the stack further down that pointed to something useful. Okay, so if we look at the stack and we say, show me like 100 pointers that are coming off the stack, you can see here, like this points somewhere in code, that's somewhere in code, these are all somewhere in code. What we're looking for is a pointer that points to somewhere that's in code inside a library of interest. Now this one here, for example, we can't necessarily rely on this one because we're probably going to clobber that ourselves when we put more ROP data into our payload. Whereas further down, like as you can see, there's a lot more pointers around here further down. Further down, we would hope that something like this would point into something more useful. So looking at code sections, we've got libc here, we've got VDSO here. So here, for example, 77BA, 77D, now that's too far. 77C is too far. So this is what I did, is I went through and I was looking at pointers going, are there any pointers here that I can use to find out, like to actually leak an address off of the stack. And so what I ended up doing, according to my original attempt, was I dereferenced off the stack and 64 pointers away from the stack and pulled that value out, and 120 pointers from the stack and pulled that value out. So that's what I was doing here. And same story here. Now if we dereference those, what do we get? I have no idea what that points to. And these obviously are just pointing to somewhere I look, or it looks to be probably inside something like an environment string. What are you guys talking about? Now I remembered where I know this name from, the Metasploit exploit writer. Indeed. Okay, alright, so first thing we're going to do is we're going to leak an address, and we need a meaningful address, and that's what I'm currently trying to find without blatantly copying and pasting my previous work. What I'm trying to find is a pointer that will point somewhere that we can then use to find the data that we're looking for, which is effectively just a syscall. Let's see. What we could do is use searchmem or ref search. Is it ref search? Ref search. We can say we want to find a pointer to VDSO somewhere in memory. So can we do that? That's not. Let's just do it from anywhere. Okay, here we go. This is interesting. All right. So what I did here is I decided to use instead the current ref search feature that's in Peta that says go and find me something that points to this. Yeah, the reason why I was looking at that is for two reasons. The first reason that I thought it was environment is because it contained ASCII that looked like it had slashes and equals and things like that in it, and purely based on the memory address as well. That's why I thought it pointed to somewhere in the environment. It was blatantly a guess, but I'm going kind of off prior experience and kind of not. So anyway, the start of VDSO, which is a code section, is in here, right? So we can actually leak this from the stack. Now what I'm going to do, given the time and the fact that I'm going to change it very, very slightly, is I'm just going to leak this address, and then I'm going to use this address as an offset for this other thing that we found before that points directly to an int80 call followed by a bunch of pops and a ret. And from there we're going to use that just as a basic offset calculation to invoke our syscall rather than using a memory scanner to do this, because we're going to do a sort of enough double buffering. This means that the exploit that we end up with will work on my version of VDSO. It won't necessarily work on a target. I'm doing that purely for the sake of brevity. Okay, so if we look at the registers at the moment, we can see the ESP is FFA, but EDX points to something interesting. EDX points to 88, so it's quite a way away from here. What we're looking to do is find any of these registers that we can use as a base in order to dereference to find this address. So, for example, EDX is not too far away from this memory address here, or this memory address here, in order to sort of double hop, right? So we've got F778 and F77E. Now looking at our memory map again, what can we rely on here? So EDI F7787 is inside libc. Well, that's interesting. That's at the point of our break. EDI points to libc. From there we can say, well, we can quite easily do an offset calculation to figure out where the base of libc is. Okay, so in doing that, that opens up another number of possibilities, but I'm going to stick to stick to the ROP option for now, I think. Maybe not. What I'm going to do just quickly is I'm going to kill the music, because my ears are very hot. It's very hot in here. Kill the music. Okay, so what I'm going to do is I'm going to look to find a way of actually gathering this address out of memory by looking at pointers that we've already got access to. In order to do that, though, we need to be able to leak. We need to be able to leak addresses. Now, what I did, like I said before, was that I used printf. And I wrote a format string to memory, and then I used that format string as part of a printf call. Okay, so that's what I'm going to do here. So step one was call getS because that allows us to write. So what I'm going to do is we're going to write a printf string to memory. Okay, I'm going to leave it at the payload address. So we call getS, we call pop EBP to skip over the payload address, and then we end up at our next sort of phase. Okay, so that means we've been able to write something to memory. Which means after we've sent this buffer, we need to send what will be a format string. Now, going off what I had here, after sending that, the first thing that I sent was $64. So that means index 64 values beyond where the current stack is. And string format hex with 0 padding and print that to screen, and do exactly the same thing with 120 followed by a new line. Okay, hey swappage. So we're going to write that to the area of memory that we know is read-writable, and then we're going to call printf with that value. So what we need here now is call printf with the format string. Okay, now the printf with the format string should cough up some data that we're looking then to read back, and hopefully that'll give us some pointer values. Okay, so let's printf, and we're only going to pass in the format string address, which is the payload address, but then after that we will need to pop EVP again, so that we jump over the value that we've given it, and that should continue to read further down and pull a value off the stack that's actually meaningful to us, that we can then use as a point to start searching for data in memory. Okay, so at this point, what did I do? I had... What did I do? I then... Oh, that's right. So at this point, in order to be able to start reading that data, I need to send the payload and read it back. But then at that point, the problem that I've got is we need to be able to pivot the stack to another area where we know we can write the next ROP chain, which is going to allow us to do another call that will allow us to read data from memory. Okay, so what I'm going to do here is as soon as the printf has happened, we will, for now, we'll stop and we'll just see what it does. Okay, quick break, continue. Yes, I'm going to need the address for printf, aren't I? I've done it again, but at least I recognized it this time. Back here, where was it? Get s. Printf is 410. Sorry about that. Alright, here we go. So we call ret and we go back to getS, which again is going to lead us down this garden path of I hate this part. What was it again? Finish. Thanks, Justin. Pro tip, when you're ROPing, finish doesn't help. But anyway, let's do it again. Break there, and the next address I'm going to do, so when we've called getS, we're going to also do this pop EVP address. So I'm also going to put a breakpoint here. Okay, so let's continue. Alright, so this is doing the getS thing. I've put a breakpoint on, what is it, this pop EVP, I think. Yep, I put a breakpoint on this next ret here. So we're going to skip over the entire cluster that is getS. And it should break at pop EVP. Okay, so this is good. As you can see, we now have a format string in memory at the appropriate location. So this is cool because we can abuse that with our next call to printf. So as we can see, we're now in printf in the PLT. So we're going to go off and we're going to print two values out and then return. So I'm going to continue again, and we're back at our pop EVP. But over here you can see we've got 2 pointers that have come out. Now, according to our VM map, FFCD90CB is, these are stack addresses. Now, why are they interesting? I don't know. Let's have a look. I don't know. But the point is that using printf, we have the ability to leak pointers, which is clearly useful to us. The problem we've got is that we currently don't have the ability to leak a pointer that's particularly useful. So that's what I need to figure out before I move on, I think, is why is it that that particular pointer at that time is useful. Now, it could be that at the time that it's called, I had actually done way more printing of stuff, or I had somehow modified the stack in some way. But according to what I had before, that's not the case. I'm literally doing a getS followed by a printf and then another getS to write the next payload. But we haven't even got to that point yet. We're literally just going to say, leak a pointer that is reliable. But those 2 pointers are clearly not reliable. So instead, what I should probably do is look at the memory around these things. 16 WX. Yeah, so this stuff here, these look so much like strings. Oops. There you go. Food. That's clearly environment stuff, which is what I thought it was when I first looked at it. So with that being said, that's not particularly helpful. It looks like we've gone sort of well beyond anything useful there, which is why I'm wondering, according to my previous exploit, that I actually bothered to do this, because clearly those pointers were being used. Looking at my previous attempts at this, I read that data in, and then what do I do? Okay, so we get a stack pointer, and according to this, that first pointer is a stack pointer, and the second pointer should be a pointer into VDSO. So somewhere around here, there should be a VDSO pointer, which I think is not the case. So what I'm going to do at this point is I'm going to quit that again. I'm going to do the quick rinse repeat. Set the 2 breakpoints that I have. In fact, I'll probably just set the second breakpoint. Continue. Now the reason why I'm setting it at the second breakpoint is because at the moment we do our printf call, which is here, I want to see what's on the stack and see if there's anything on the stack that points to something inside, one of these code sections. So on the stack here, we've got 77600, so that's again read-write. We can use that as a base, like we said before. Maybe that's what we should be doing. We can use that as a base to leak the address of libc just by doing a basic offset calculation. And from there, we can then sort of do a second ROP with a generated searcher that we can then use to locate the int 8 that we're actually looking for. Further on though, let's have a look again at, see what else is on the stack, because further down, once we get down this area, this stuff is probably fairly useless to us. But these bits here, like this one, these pointers here are much more useful. So F77, yeah, exactly, Justin. I'm looking to put another ROP chain in for sure. So FF7AB, FF7 is in here. Now we know for sure, when I did my search mem before for OX C380 CD, that LD is where I found it. So this one here, for example, we know that if we leaked this address here, this one here, FF7A AB, that's really close. If we leaked this address, we could do a basic offset calculation from here to here. Okay? So if we go, that's 1, 2, 3, hang on, where are we? This one here? Yeah, this one. So we've got FC 1, 2, 3, 4, 5, 6, 7. Sorry, 1, 2, 3, 4, 5, 6, 7. 7 lots of 4. So there's 28 addresses, 29, 30, 31. Okay, so if we, instead of doing that, we just did 31. Hopefully that will literally leak this pointer here. And this pointer, as we can see, is that minus whatever this baby is here. So that's an offset to the beginning of LD. But we also know this address. So if instead of that we did this, and once we've leaked the address, we add that amount, then we know exactly where in memory our syscall instruction is. Okay, so I'm going to continue to pursue the path that is kind of specific to my machine rather than doing the memory searcher, based on the fact that this is still taking me quite a bit of time. So I'm going to do this. I'm going to say LD syscall offset is that. When we do this, we then need to be able to do a get s to read it again. Okay, so if we did this again, so we read it, we print it, and then the next thing we need to be able to do is generate another ROP chain. So we send our buffer, we send the printf. The next thing we're going to have to do once we've sent the printf is read. So we need to be able to go s, let's just get rid of that, s dot receive. Now, looking at what we had here, when we switched to interactive mode, we're probably going to need to ignore a line and then go s.recv what will be 8 characters. Those 8 characters should be the full address that we've just leaked. So let's just say print, we're going to need this, So we're going to read that, and then we're just going to print it out. In fact, I'll use own.log.info leaked. I should learn to type. Leaked address. Okay. So we're going to just move ahead with what we've got here, because I want to see if the actual leaked address comes out correctly. I'm not even going to bother attaching. Yeah, I'm going to need to get rid of this. Whoops. Okay, so what happened? Did we get to where we were looking for? No, we didn't. So we called rect_v line, and that clearly didn't work for some reason. Maybe we should assume... check it out. Leaked address was F76 blah blah blah. Okay, so what I'm going to do is run that again, this time attached, because we want to actually check those addresses. Let's quickly add a breakpoint. Is there any questions going on here? Need to go now, thanks for the... Okay, cheers mate, thanks for coming along. Continue. Go. Do your thing. Okay, so we've got our second breakpoint. We've got a leaked address here. Let's have a look at the virtual memory map. F7707 FCC points to somewhere in here. Is that right? Yeah, it is. And then what did we decide to add? We were adding something to it, weren't we, which gave us access to something further on. So our offset calculation is way off by the looks. Let's go back to the values that we had up here when we were looking at our VM map. So we pulled this value out, which is AB inside here, 410. And unfortunately that is not, that's fine. It looks like we may have missed it. B8FCC, that's in here. So maybe we've gone too far. That might be what's happened. So let's run that again. Set the breakpoint, continue. Okay, so that's useless. Absolutely useless. But that, at this point, should at least give me something that I know I can look at as far as stack addresses go. So let's have a look. We'll go through another 100 stack address pointers. Right, so originally maybe I was getting something like, I took 2 off, so it's probably gone from not from here to here and not from here to here. Did I take 2 off? No, I added 1. That was stupid. Add 31, and what I want to do is add 2. Yeah. Quick look again back here. So we were trying to pull this one out, and it looked like I missed it, so I wanted to subtract 1, but it looks like I might have added 1 instead. Which means I would have gone from, not from there to there, probably from there to there. 75 F6. Yeah, that's what I wanted to do. Let's see what this gives me. Connect, breakpoint, continue. Yeah, okay, that's better. Right, just before, let's get back to here. And again, I'm just going to do a quick check for what is going to be X, WX, ESP plus 30 lots of 8 bytes, right? Which is 240 bytes. Is that right? I'm doing 30 lots of, they're not 8 bytes, it's 4 bytes. What am I talking about? 30 lots of 4 bytes is 120 bytes, which gives us that. F77E410, F77E410 lands us in here. That's exactly what we want. Okay, so if that address, that F77E410 comes out, which it doesn't, then we'd be laughing. So clearly at the point that we do our printf call, we're still off very slightly. So let's go 124, 116. Now, is there anything at all resembling this? There it is there, 24B9. And what we are looking for, what we want, is 410. So we've got to subtract another one. Okay, so that needs to be 29. Okay. Oops. Right, continue, run, continue. Okay, so let's have a look at the VM map now. F779A410, F77. There it is, it's in there, fabulous. Okay, so that's given us exactly what we're looking for. We've got our leaked address. We now need to convert that back to an integer. Which isn't so much of a problem because we can just decode it as hex and do the byte swapping thing. So we know we've got our leaked address at a pretty reasonable location. So instead of call it add string, we'll call it LD address string. So that's what that's going to be. We then need to go LD, not LS. Okay, so syscall ret address should be the LD address string decoded into hex, which should give us the bytes sort of in the wrong order. So we then need to reverse it and then unpack it. Okay, so clone unpack 32. It's pretty dirty, I know, but we've converted those back to bytes, spun it, and then kind of respun it while unpacking. And then we're going to add the LD syscall offset to it. And then from here we should be able to call hex of syscall red address. With a bit of luck, that would tell us exactly what we're looking to find out. Who's excited? Okay, so if we fly by the seat of our pants and say, show us instructions at this point. Oh, yes. Boom. Okay. So we've kind of, like I said, we are kind of hard coding this in a way that's specific to my system based on time. But as you can see, we've leaked an address into the LD library, and we've used that as an offset to figure out exactly where our syscall can go. So now that we have the ability to do that, we now need to do two more things. We need to write a payload, our shellcode payload, to memory, because that's what we're going to execute. Okay? So at this point, let's have a look. We want to undo this again. That's going to be the next thing that we do. We want to write our shellcode payload to memory. So after that printf, so this is send of original buffer. This is send of the printf string. Here we're actually figuring out the syscall location. And then we need to send the shellcode payload, which is going to get written back to the payload address. Okay, so that means we need to go s.send sc. Remember, we've got our shellcode payload sitting there in memory already. It should be just up here. There you go, we've read that shell in. Which means we've then written our payload back to the start of the payload section. But the next thing we need to do is we need to have a ROP chain written to somewhere else in memory that does the syscall for us. So what we'll have to do is we'll choose an area of memory that's nowhere near our payload. So let's go, we'll call it second ROP address equals the payload address, and we'll move it over, I don't know, the payload's not going to be that big, so we'll just add hex 100. No, let's make it further away, that scares me. Let's make it 400. Okay, so that's where our second ROP gadget stuff's going to go. Alright, so now what we need to do is we need to do another read that reads our second payload back into memory. And the reason we have to do this on the fly is because we've actually only just figured out the address. Okay, so that writes the printf string. Sorry, no, this doesn't write printf string. This writes shellcode to memory. Okay, so that puts it in the payload address. That means our shellcode will have overwritten the printf string once it's done. And then we figure out what our address is that we're going to return to. We send our shellcode. It's then going to ask us again for the second ROP. So write second ROP to memory. Okay. So here, instead of using payload address, we need to do second ROP address. Yeah? So with our second ROP, we then actually need to pivot at that point. Now the good thing is that taking this approach means that when we pop EBP will point directly to our second ROP. So we should be able to do a leave rep combination, and that will pivot ESP to where EBP is and return, which should result in our second ROP chain from actually being run. So we go pivot to the second ROP chain. So we basically need a leave ret instruction, yeah? Leave ret. Sure, there's plenty of those. Here we go. Here's our leave ret. Need to chuck this up here with all the other bits and pieces. Leave ret address. This doesn't. Whoops. Is anyone asking questions? Nope. So we've got our leave ret address, and from here, as soon as we finished, we should be able to just say P32 leave ret address. Yep, okay, that's cool. So at this point, we have everything we need except for this. Now, the pointer, remember this buffer, which we now need to restart because it's fresh, this is what we're going to send as part of the last read. So when we do this ROP, the pointer that we're passing in is actually going to be the payload address. So we're marking the payload address as read, write, and execute. Okay, and then when the payload address when the payload has been marked as executable, we need to pivot to it. So there's a number of ways that we could do that, and it will probably depend on whether or not EBX, which is this register here, still contains the pointer to the memory that we've just changed. Do we have a jump call thing in here that does? No, not call E. We need to be able to jump to what's in EBX, but by the looks of it, we don't have those gadgets available. Is there a jump EBX? Call EBX? No. So what we're probably going to have to do is another stack pivot. So what we'll do here is instead, see how there, we'll do a pop EBP ret, okay, because this means we'll be able to put our payload address directly into EBP, and then pivot to it. Is that right? No, that's not right. That's not right at all. We can pop into EBX and ret, we can pop EBP and ret, we can pop EBX, ESI, EDI, and ret. But we need to be able to call, we need to be able to call a register directly, which means we also need to be able to get a value into that register before we call it. We could do yet another pop AD call. That's probably an easy option. How about we do that? Let's be lazy. Let's do another complete destruction of registers. We don't need to do anything other than set a call instruction. Which we've already got a call EAX, and we have the ability here to put a value in EAX. So how about we put payload address there. Now I'm just going to get rid of some of these comments to make it look like I do actually care. Okay, so I'm being super lazy here because I'm doing a full pop of all the registers again immediately after just doing it. purely so that I can set EAX, and then when EAX is set, we've got to call EAX address, which we can shove at the end. So that means that our actual shellcode should execute. Whew. You can't just drop the address of the second ROP chain into your first ROP chain. Yeah, I probably could actually. You're right, I don't actually need to do the pivoting, do I? I don't need to pop EVP ret at all. No, you're dead right, mate. Why did I do that? I guess at this point, that's exactly the same thing. But I'm going to go with what you've just said. Instead of no, fuck it. I'm going to leave the pivot in there, just so that there might be learnings involved. Yeah, let's do that. But you're right, Justin. You're definitely right. You should be able to just return to. Oh no, you've got yeah. No, sorry, you can't. You have to do the pivot because you need to modify ESP. Yeah. Yeah, I've got to do that because I've got to modify ESP and I've got to continue to pop. So, all good, all good. Okay, so then when we're done, we need to send that buffer as part of the next thing. Okay. Let's see what happens. Run the exploit, attach. I'm going to put that breakpoint on the EVP pop again and continue. Let's go. Okay, so here's our first printf call. Printf leaks this address, which I haven't used. I haven't used. So I'm going to restart this because what I need to do is actually execute the syscall. We've got to do the syscall ret address. So now that we've calculated it, we can actually bake it into our payload. Sorry about that. So after our first sort of pop AD, we need to do a syscall, then we're popping AD again and just doing a straight call. TS Jost. That's a pretty deep question, buddy. What I reckon we should do is, so TS Jost has asked about, you know, if you're a programmer and you want to get started in reverse engineering, where do you go? I think it's probably worth writing a blog post or having a chat on IRC or something outside of this. So rather than answer that question now, but I'm more than happy to help point you in a few directions to get you going, including watching more streams like this and stuff that Justin's done and just playing with stuff. But so for now, that's all I'm going to say, but we can definitely talk about that a little bit later. I hope that's okay. Right, set our breakpoint, run. Okay now. So, we've leaked our address. Let's just validate that this address is still doing what we want it to do. There it is, int 80. So, let's go to the next instruction. So here we're doing another get s. So the get s, thankfully we're constantly coming back to the same pop EVP ret. So we should be able to continue and break again. At that point, the payload should contain something a little more interesting. So let's have a look at whatever bytes are currently in memory. Now that certainly looks a lot like our shellcode, doesn't it? So let's just have a quick gander at that. C stream xxd shell. There you go, DA D1 BBA3, DA D1 BBA3. So our payload is currently sitting in the appropriate area of memory. So that's good. Ret, where are we going to now? We're now doing get s again, and this time we are writing to this area of memory. Alright, let's have a look at the next 100 bytes of this. So that looks like arbitrary garbage. I don't know whether that's useful or not. But again, we're going to end up at a poppy VP ret, so let's run it and check this out. What do we got here? We should probably look at this as words. Okay, so this looks like, here we go. See, there you go. This is our pop AL happening. Okay, so according to this, the next thing we're going to do is a pop A. So check out the content of the registers in just a second. So we've got to our pop A. Now, what has happened here? Oh, that's right, we're now stack pivoting. So we've got to our leave, which means the stack and EBP, so here you go, EBP is pointing to that payload. This is the reason why we needed to do it, Justin. So leave ret pivots the stack to the payload and then pops. So we may well have failed because EBP is popped immediately beforehand. Right, so when we call ret, we actually want what's effectively a ROP not to go in here. So if it gets executed, it doesn't matter. Home.p32 ret address. So this means when it actually pivots here, these 4 bytes are ignored. So what I'm going to do to cheat is I'm going to set ESP equal to ESP minus 4. So that's kind of doing a very small stack adjustment. I could probably cheat and do much better than that, but for now, just assume that I had actually put those 4 bytes where they belonged. Okay, so now we're at pop A, which means we should see all of our registers change. So after this, we want EDI to be 0. So this will be 0, this will be 0. EBP should be 0. ESP is ignored. EBX should contain a pointer to the payload, which is this address without the 4. EAX should be 7D. The ECX should point to like 2 pages worth of data, and that should be it. Alright, that's looking good. Check that out. And so CLD isn't really a problem in this case. It affects flag registers, of which we're not particularly interested in. And so when we ret, we should pop to the syscall, which hopefully works, but it didn't work. So the syscall executed, and you'll see here that it returned in EAX an invalid result. So the syscall actually failed. So that could be because the parameters that we've passed in are incorrect. Let me just check. 7D is definitely what we're putting in EAX. I'm guessing it could be the fact that we've actually got 2 pages worth of data being marked, and we don't have 2 pages worth. So I'm going to change that back to 1, and I'm going to run it again. Breakpoint, where are you? Here we go. Go. Okay, I'm going to fast forward. Now what we should see, where are we here? We're about to do our leave ret. Ooh, I went way too far. Sorry. My bad. Okay, so this is now doing another getS. We should be able to do another one. Yep. Get S. Okay, so here's our stack pivot. So we leave. We call ret. And we get our pop A executing. Here we pass all the values which appear to be correct, right? So we care about EDX being set to 7 because that's our memory protection constant. ECX should be our memory address, our page size, the number of bytes that we actually want changed. And EBX points to the area of memory we want to change. I may actually be making one more mistake, which I'm just going to check in just a minute, but let's see what happens when we execute our syscall. Ready? It worked. Look, EAX returned with 0. Excellent. Okay, so this means that if we do a VM map, we should see, here we go, look, our area of memory containing our payload is now read, write, execute. Hooray! So, stepping into this, we do pop A again. Why? For some reason, our call EAX address. Oh, yep. So EAX points to a call EAX instruction. EAX points to. Why have I got an invalid PC address? What did I do wrong there? CLD ret. Oh, I need a ret. Okay, so what happened was EAX points to the appropriate location. CLD ret. So when we call CLD, that's fine. We then call ret. You'll notice that ESP has changed. It's not got anything useful in it. So how did that happen between here? So we did all our pop A. We still needed our call EAX address instruction to be in like immediately after our pop. So we failed somewhere. For some reason that call isn't there. Now looking at what's at the end of this payload, we can see, going back up here to where the stack finished, so we can see pop A, and then as soon as the pop A had executed, this is the content of the stack. Now why is that the case? It looks like something is maybe accidentally written here that's out of our control. 253C. 25%. What's 3C? Don't know. But anyway, clearly something shady is going on. We might have to reduce the size of our payload very slightly, or we can write our secondary payload to a completely different area of memory. So let's do that instead. Let's change our second ROP address so that it's here instead. So we're just going to shift it back in memory in the hope that that's actually what's causing the problem. Okay, the shells are coming, guys. They're coming. I can feel it. Okay. Continue. Continue again. Pivot, ret, pop A, CLD, ret, change memory, pop A again, pop A, CLD, okay, so something is actually changing the stack. So we pull all those, and that's okay. We seem to end up with EA. Oh, okay. See now, again, that's just me being very, very silly. Call EAX address needs to be at the end, but we actually need our payload address to be in in EAX. So we were off by one. So instead of putting the payload address in EAX and going call EAX, we were putting the call EAX address in EAX and not backing it up with anything else. That makes a bit more sense. Here we go. Boom! Shells. We got shells. All right, let's debug this again. I'm just going to quit that. I'm going to quit that, and I'm going to show you again. Let's attach. Let's hit that breakpoint again. Continue. Okay, so we'll go past that first 3. Okay, so what's happening here now is, if we take a look over here at our exploit, we're about to invoke this leave ret. Okay, leave ret does the pivoting of EBP and ESP, right? So EBP currently points to our second ROP chain, and our second ROP chain is all of this. This is the thing that we generated on the fly. Okay, so leave ret, leave should say take whatever's in EBP and write it to ESP. So here you go, you can see ESP and EBP are not the same because ESP was set, EBP was set to ESP was set to EBP, and then the value off the top of the stack was popped into EBP. So that's it doing its stack adjustment. And so you can see EBP contains a ROP NOP, it's just a 4-byte value we don't care about, and ESP now points to pop A. Okay, so when we go ret, we go to the pop A instruction. We call pop A, we completely populate all of our registers with a valid syscall saying, please mark one whole page of memory starting at our payload location as read-write executable. So that's all looking good. We found our address in memory for the syscall we were looking for. If we look at our VM map now, we can see this is where our payload is stored, just in here, and right now it's only read and write. Whereas as soon as we finish this syscall, it's now read, write, and executable, exactly like we were hoping. So then when we return, we pop A again because we're lazy, and we can see that EAX points to the payload. Okay? When we ret to this call EAX instruction, which immediately passes control to our payload, which at the beginning is at the beginning of that read-writable executable section, and then when we run from this point on, we end up with a broken shell because we debugged it. But clearly it works. Okay, so I took a slightly different diversion with this second one compared to what I had intended to, because we were getting on time-wise. But what I can tell you is this. If you look at how we had broken up our ROP chain into 2 sections, and we wrote our first one to the stack and then we pivoted to a different area of memory, what I did with the previous one was using printf and puts, a continually buffered sort of back and forth, scanning memory, looking for a sequence of bytes. And when I found those 3 bytes that I was looking for, the int 80 followed by ret, when I found those 3 bytes, that's when I was able to calculate exactly the location of a syscall ret that I knew that I would be able to use locally. Now the problem problem here is the approach I've took is very much tied to my local setup. When you do the sort of constant double buffering generation of ROP chains to read memory on the fly, you know that wherever the hell else it is on the internet, on whatever machine you happen to be running on, it's going to find a valid instruction on that target machine. You don't need to know what version of libc is running or anything like that. It will just work. So we rely on pretty much nothing other than the ability to find a syscall instruction on a remote machine. But given the time, I'm not going to go any further. So for now, it's fair to say that it is possible to leak addresses based on offsets. If you're able to determine the version of libc that's running on the target, you can take the exact same approach that I've taken here and just do an offset-based calculation. And the last thing that you can do is you can use the pwnlib dinelf library. The dinelf library is really, really cool. You can give it a function that leaks a single byte, and it will tell you exactly where system is. And then you can literally ret to system with a string that you've already written to memory, and voila. So anyway, let me have a quick look at what you guys are chatting about, because it looks like Justin's thankfully taking over the reins when it comes to explaining people in the chat. So thank you, Justin. Bit of a discussion around what reverse engineering happens to be. Programmer, a couple of books worth referencing. Yeah, Art of Software Assessment. That is a piece of a book. GUI reversing. Talking about software licensing. Shells. And there you go. We're done. Okay. Look, I think I'm going to leave it at that. I will make these things available, downloadable, etc. I appreciate you guys listening and sticking with me as I fumbled through. As you can see, the mere addition of NX does change things quite a bit when it comes to a binary that's this small, but it doesn't mean that in any way it's not possible to own it. So yeah, thanks very much for listening, and see you guys later.